and welcome to the recording of day 2 of the Scientific Python workshop. In this video, we're going to go over some elementary libraries for scientific computing, starting at plotting, then some data handling, and towards the end, we will look at SciPy, and we will also start a little bit on the Scikit-learn section. If you missed day 1, you will find a link to it down in the video description to go over to the Musen YouTube channel and watch it there. So I hope you'll enjoy this video. Okay, so yesterday we looked quite a lot over the basics and also the question why you should be learning Python. And the bottom line I want you to, or the main takeaway for you should be that Python is both a slow and a fast language. So in itself, like using the native components of Python, especially for scientific computing and machine learning, is extremely slow. It also quickly reaches a point where it's just infeasible to practically use it. But when we use clever libraries like NumPy that avoid the slow concepts of Python, like for loops and while loops and all those kind of things, then we can achieve quite a good performance, especially some libraries that work on top of NumPy. We don't look into this workshop in more detail, but which can give you even more performance boosts. I will highlight them a little bit in the outlook in the end of the day at the end of tomorrow's day, at tomorrow's workshop. But in the end, you kind of can achieve competitive performance compared to really low-level languages like C, Fortran, and so on, while still retaining in this high-level set of features, which is quite advantageous, first of all, from getting your job done quickly. Second of all, it's also, at least in my opinion, more readable than having hundreds of lines of code in C or C++ or Fortran in order to solve a problem. And it also lets you interface with many other things more easily, especially when it then also comes to data handling, which can be more difficult, and it's probably not often done within these lower level languages. And of course, this is not necessarily an intricacy of Python. I mean, you have the same idea in MATLAB or even Julia, maybe a little differently in Julia then. I think it's also the same idea in R, in case you are familiar with that. So R, that's a language for statistical programming. Why I want to advertise for Python in comparison, for instance, to MATLAB is that it just has a vaster ecosystem. And on top of MATLAB, it's free, which is the first advantage is, okay, well, I don't need a MATLAB license. But the other advantage also is someone else does not need a MATLAB license. So the code that you write is also freely accessible to everyone else. Basically, he or she just has to install Python on his or her machine. That's kind of what I think is a really high value, especially also when it comes to performing scientific research that involves software, when you have something that is easily reproducible. Okay, never mind, this was kind of a long advertisement. I'm pretty sure there are also really good use cases where you rather want to use MATLAB over Python, but I think this is really a strong advantage of Python in that regard. Either way, we looked at some elementary aspects, data structures, and so on. And then the second half of yesterday was on NumPy. I hope I was able to give you a good overview of NumPy. And again, the essential aspect is using these NumPy arrays. So expressing array-based operations by using abstractions that allow us to move for loops and so on into the NumPy library, and thereby obtaining competitive speeds. And concepts that NumPy uses are, for instance, vectorization, such that you can have functions that apply to all the elements in an array. And for instance, we looked at the example, if you remember, like applying the sign function to all elements in an array. And we could achieve like a 10-fold speed up just by using NumPy in this super small example. And the difference becomes more prominent if you reach larger sizes. And then we looked at some more advanced concepts like broadcasting and reshaping. And in case this hasn't clicked with you yet, don't worry, I think we will see it over and over the next sections. And then we also looked into linear algebra. Probably the examples I came up yesterday with might have been a little bit abstract, but my general perception of linear algebra is that most of the examples you can come up are rather abstract, although you always find use cases for this. And the bottom line is just that all the functionality that you are used to from other languages where you do scientific computing is available within NumPy. Well, I say all, of course, probably not all, but the most important stuff. Okay, then let's continue. What are we going to do today? So we will look into Matplotlib. which is kind of the super easy and probably also a little old-fashioned way of doing plotting in Python. It has an interface that is quite similar to how you do plots in MATLAB. So those, if you are familiar with those, you should become easily familiar with Matplotlib. Then we will look at Pandas. Pandas is a library for performing data-intensive tasks. So for instance, handling databases, handling CSV files, all that kind of stuff. And then we will look at Seaborn. Seaborn is a library that builds on top of Matplotlib and kind of offers more convenience features, and in my opinion also has a more modern look, especially from the color palettes. Afterwards, we will look at Plotly, and Plotly is kind of a really, I mean, it's not a new way anymore. It's any longer. It's been on the like the Python ecosystem for a couple of years now, but it's kind of the more recent approach into how to do plotting in Python. And it also greatly differs in its interface, but it has a way more usability or maybe more functionality. So we will look into that in more detail. And then afterwards, we will look at something that is really close to my heart, which is Streamlit. And that's relatively new, I think it's only 2 or 3 years old, Python library that allows you to easily build interactive web applications usually for machine learning and scientific computing applications. So we don't build like your personal website, which portrays something about your work or something like that, but rather what you can use in order to convey the findings of your research to someone else and make them accessible interactively. I'm pretty sure you will like that. Afterwards, we will look at SciPy, and SciPy is kind of NumPy on steroids, if you might say. So it kind of uses NumPy arrays, but has many, many more algorithms. So NumPy itself only has a couple of linear algebra algorithms and a little bit of fast Fourier transformation, but SciPy kind of has the collection of all the algorithms you might be familiar to if you come from MATLAB. So this, for instance, includes sparse matrices, optimization algorithms, root finding algorithms, you name it. And we will look at a small overview because it's just impossible to cover all of it. And this should give you like a glimpse of how the library is designed. And we will put some particular emphasis on the documentation of SciPy, so that we look into the documentation together and try to understand how you can get meaning out of the documentation, because as with so many things, it's just hard to convey really good best practices to it. You tend to have to figure this out for yourself. And therefore, I just want to give you like my way of approaching this, especially when using the documentation. And then depending on how fast we progress, we might even already start with Scikit-learn, or we move it to tomorrow. Okay, great. I hope now everyone is feeling good for our coding, so that let's go down to the actual stuff. Let me see, I think it was about page 70. No, it was not. Never mind, let's just scroll down. Okay, so let's go on to Matplotlib. And I already mentioned that Matplotlib is a way that, and then there is a good question, I just want to mention it. How does mixing libraries work? For example, SciPy and NumPy. And then in brackets, we'll probably learn that today, right? Yes, we will learn that. And it's interesting. In the end, for many libraries, you kind of have to be aware that the interface might differ. I think the interface between NumPy and SciPy is super straightforward, since SciPy builds upon NumPy arrays. Although this is kind of probably also a big, but it's great that you mentioned that. This is probably also one of the bigger disadvantages of Python. I already highlighted that a bit yesterday, but since there is not one commercial vendor behind the software, like with MATLAB, it's MathWorks, which designs certain toolboxes and designs certain interfaces, you kind of see a lot of open source developers developing different libraries. And as people in the software developing world are, they tend to be opinionated about something. And this can be, for instance, the interface design. This can be certain conventions. And it does not necessarily mean that one thing is better than the other. But the problem for you from a user perspective will be that it kind of feels inconsistent at some points. And of course, this is just like a consequence out of this fact that you just have such a vast ecosystem, and that you have these different mentalities of the developers. I will try to highlight that at certain points. I mean, for the libraries we look at, I mean, we will see that at some points the interface looks different. There is no one best practice though, but good that you mentioned that. So I will try to focus on that from time to time. Let's go on to Matplotlib. And for this, we just want to start super simple with some line plots. And for this, I want to refresh in case you have never done that before, but I'm pretty sure you at least have done some plots in Excel, how to draw on a computer, at least for line plots. And the first task I want to do together with you is to draw a sine function. And for this, what we're going to do is, of course, we have to kind of sample the sine function at certain points. And here you see 3 different curves. Let me take a different color. And here we've sampled the sine at 8 points. So we, for instance, sampled it here, 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 and here. And then basically what Matplotlib or any other drawing library, or I think most of the other drawing libraries would be doing, is to draw straight lines in between those points. And then, of course, this blue is a rather rough approximation. If we use more points, then we get the orange, and it's getting closer towards a sine function. And if we have many points, I think this was 100 points here, we kind of, at least from an I norm, we kind of see this almost feels like this smooth sine function that you might be used to if you draw it by your hand. Let's just do that in Matplotlib. For this, I would like you to go to Visual Studio Code again and expand, to, if you haven't started it yet, so it should be looking like this again. Maybe it has remembered your open tabs. If it hasn't, no problem. Then we want to use the terminal. In case it is closed, go down to the action bar just right above it, and then your cursor will change into something you can drag up. And then we have our terminal here. We can maximize it. And in case you're not in your, Conda environment yet, then do Conda activate Python course. At least for me, under my Linux bash shell, you should get an Python course in brackets right before the printout statement here. Okay, then let's enter the interactive Python shell again with IPython, and then let's go to Matplotlib. And as kind of this theme for most of the activities we're doing from now on, we will always use NumPy. So because we need these NumPy computations, and so we will first import that. So import NumPy as NP. And then we need Matplotlib. So we do import Matplotlib. And remember, like with tab, you can get the auto completion. Matplotlib. And then we need this particular interface. Matplotlib has a couple, but I think the PLT, the pyplot interface, is the most useful here. So import matplotlib.pyplot as PLT. And maybe also as a quick refresher, yesterday when we imported stuff from other files, this dot syntax was giving us access to the submodules, which kind of were hidden in subfolders. So in case this rings a bell again. And this is a common variation. I think we also talked about that yesterday. So there's like some, let's say, loose conventions on how to import things. And usually it is import matplotlib.pyplot as PLT. That's what you see in, I would say, 99% of the cases where you read code online. And if you have any import errors here, you might have not installed Matplotlib, but I'm pretty sure every one of you should have it. If that is not the case, well, then what is the best thing to do? But I'm pretty sure then please let us know in the chat. That would be pretty helpful if you have issues with that package. Then let's continue with with our plotting. So for this, we have to kind of create a table of values. And for this, we have to create a NumPy array, which basically contains our X values and our Y values. And we can use the creation routines from NumPy in order to do that by saying, for instance, X is NumPy.linspace. for linearly spaced, we want to cover the entire sign. So we want to go from 0 to 2 times numpy.pi. And remember, all these constants you might be familiar with are in also in the scope or in the namespace of NumPy. And then we want 100 points. So basically, this is now a one-dimensional array, or sorry, I forget again, a one-axis array with 100 dimensions in the first axis, to be precise. And these are just linearly spaced values. So you see the spacing in between them is equal, so approximately 0.06. And then we can create the corresponding y values, or we can query our sign by just applying numpy.sign on x. And also remember that here we are using a vectorized operation. We could use the for loop where we would iterate over all the entries, apply the sign, and then save it in an array. But we can also do it in this vectorized way. And as said, for larger computations, this is the way to do it. Then we can do plt.plot x and y. So basically draws a plot with x and y, and then hit enter. And nothing happened. Well, this is kind of the way Matplotlib decided to implement its interface. You have to first plot it, and then it kind of creates a buffer, so kind of like a background storage object where it is plotted in, because you could plot multiple things in there, and then you have to start up a window that pops out, which contains the plot by doing plt.show. And here we go. I hope you are seeing this plot now. If you're having issues with that, that can have multiple reasons though. But I hope there are not. I mean, it kind of depends on many factors if that is not working. But also if that is the case, please let us know. But here what we're seeing now, basically what we expected, we have a super simple plot without any axis labels, and we have our sign function. And it looks kind of smooth because we used a couple of points. Now I want to introduce you to a couple more plots, and we will just go over the standard stuff. And this should give you like a feeling of how these things are implemented in Matplotlib. So for this, I want you to first download the data together with me. So I already have it here. This is a couple of collections of data. And for this, let me show you how to download that. So you should be having that pet, and in there you find the material for days 1 to 3. I'll also show you the link in a second. And here you would then have the repository, which contains source code files and the slides. If you have never used GitHub before, that's not a problem. We can always download a zip file. So this is basically the zip file we're using, and maybe get copy link address. I hope this works. And there should be download link for you, such that you can then download it, open it, and then extract the file with whatever way you prefer to use extract zip files. We are mainly interested in the data aspect here. And then once you've extracted that, please copy the data into your VS Code session such that you have a folder with data here. And while you're doing so, I will just quickly show you what we have here, what we're going to look over in the next hours and also tomorrow. So we will look at some examples from the election of the German federal government, and we will look at some artificial data set that I created with a rule of which with people at certain age, whether they're getting pension or not. And then we also have some example that is kind of taken from the real world. We will look at a so-called MSCI World Index. I think we will do that tomorrow. So the MSCI World, that's a financial indicator of the global markets or the global stock markets. And yeah, and then we have a couple more. I will show you then. Okay. We can then use some, so this is basically some data. And yesterday I mentioned we haven't looked at file I/O yet. So I/O stands for input output, and that refers to reading in files or writing out files. but we want to use that kind of like on a higher level, that we want to read in CSV files or that kind of files in order to get some NumPy arrays out of that. And for this, we want to use the NumPy command generate from text. I think it will also be the only time we will be using it. Maybe I'm wrong, but this is just to show that NumPy also consists of these functionalities. There are multiple input-output functionalities. If you need it for a particular use case, I would just advise you to Google that, and I'm pretty sure you will come up with a super nice Stack Overflow post explaining the particular input-output functionality for a particular use case that you have. But here I will just use the NumPy gen from text, which stands for generate from text. So let me first clear my screen with Control-L. And then let's read in the results. So basically, I want to read in these two, which has the elections results from 2017, the different parties, and the different results in percent. And for this, let's do numpy.gen from text, and then do data, and then election results. NumPy generate from text. And then we can look at the results, and we see, well, that's an array with the percentage values in here. And then we want to read in the party's name. So the name of the parties by doing parties np.gen from text and say, well, we can do it the same way, but I want to show you something else, which is also quite neat. And for this, let's head over to your web browser where you opened the GitHub repository. Let me just quickly make that smaller so that you can still see what I wrote in the terminal here. See? And if you go to the election parties, you can access the raw file, I think. Let me see if that's here. Yeah, view raw. And then basically you have a web page where your CSV file is displayed. I will copy paste the link in the chat. And the cool thing about your NumPy gen from text, or literally most of the file IO stuff, is that they can't just only read from local files, but they can also read from web addresses. And that's, of course, quite handy. I mean, you could, of course, always download it, but that's a little bit of the shortcut. So I will copy paste it in here. Copy paste in terminal. Kind of depends on kind of shell you're using, but sometimes you can't just do Control V. You can probably always do right click and then paste. But in a lot of terminals, you actually have to do Control Shift V in order to make a paste. That is because Control V is often already a shortcut that has been used for something else. Okay, well then let's close that. So, I mean, close that, have the closing string. So this is then basically our web address. And then here we have to indicate what kind of D type we're using. So remember, NumPy arrays contain values of only one data type. And here, NumPy was able to infer that data type, so which is a floating point number. But here we want to have a string. So we do D type is str, equals str. And then we have our parties. And here we have the type of parties. And this kind of shows we can read in from multiple sources. And then let's first, okay, well, what can we do with those kind of results, having parties and with these results, with this kind of data, having parties and their corresponding results at the election. So what is commonly done, for instance, if you have TV reports of election results, you might see bar charts. So let's do a bar chart, right? Let's do plt.barchart and then come up with parties and results. And again, remember, it's first written in the buffer of Matplotlib, and do plt.show. And then here we go. At least it could look a little differently for you. That depends on the operating system you use and the backend drawing software. but it should at least represent the same scientific data. And so here we see the different results. So from the 2017 election, the bailout gave the CDU, the Conservative Party, the majority of the votes, and then you also see the other parties. There's a question on Slido asking, does it automatically recognize the website contains a text file, or does it have to be a CSV site or a similar text format? It depends. So in that particular case, the website, oh, sorry, where is it? That's the website. Let me quickly get it again. No, that's the wrong. That's also the wrong. Here we go. Here, the URL contained a .csv at the end. That's not necessarily, I don't think it's necessarily relevant here. It's more relevant that you have kind of a raw data so that it's not just a rich HTML. Although there are also some websites where Python packages can extract certain things for you, but that's of course like some kind of a convenience feature that the library maintainers and library developers included for you. This generally just refers to data that is available. Yeah. Okay. So it has to be like directly raw data in that sense, so plain files. Of course, it can also read other file formats, not necessarily CSV, but that kind of depends on the read-in routine you use. So this is rather general then. Okay, amazing. Well, then let's see. Maybe that fixed it. But I didn't do something really special there. So this is really weird. But either way, let's close that plot and let's see if I can read in the results again. So again, let me first do that with these handy shortcuts here. Parties. And then we had plt.bar, like this, plt.show. And I hope now the bar chart is visible. Can you please let me know whether this can?
Yes, it is.
Okay, that's crazy. But if that issue comes up again, please let me know so that we can, yeah, I don't know. Maybe I can think of a better fix in the break. Either way. Okay, where was I? So maybe so there was the question about the how to read data from remote websites. So I think I answered it like this, that I hope the browser is also now visible. Can you confirm, Jan? Can you see the browser on the?
Yes, there is CDU, SPD, AFD.
Perfect. Okay, great. So this is basically just some plain website that you can access at GitHub. And if you have similar resources, then you can directly load them into NumPy, at least with this command. And as I said, that are some more advanced routines which allow you to read from, also from rich websites. I think we might see them later, but yeah, in general, this is just like a convenience here that you don't have to download it yourself. Okay, so we looked at the bar chart. What I'd like to put a lot of emphasis on is at looking at the documentation of these things. So because right now this bar chart might not be too fancy here, so we might be interested in what we can do with that bar chart. And for instance, let's look at the documentation of Matplotlib by doing help and then plt.bar. And let me expand that here, the terminal, so that we have it in full size, and also close the file explorer. And then if we hit help, then we see, well, it says make a bar plot, how obvious. And then we have a kind of options here. I don't want to go into them in too much detail, but the most important one is that we have these two positional arguments that we provided with X and Y. So these are basically the positions, or basically the parties and the results that we associated here. And now we might be interested in styling our plot. And it's kind of a little bit, it can be a little bit confusing that you don't do that within the call to the bar function, but rather do this with additional PLT methods. So let's, for instance, plot the bar chart again, so using the arrows, and plot it again. And then, for instance, we might be interested in adding axis labels, and this can be done with plt.xlabel, and we can again use the tab for auto completion. And then you might be interested in calling the x label parties, and then do plt.ylabel and call this the election results. And if we now call a plt.show, and you hopefully see that, you see that there are now axis labels. And with these plt commands, you have way more flexibility for customization. You could also assign the corresponding colors to these parties that they usually indicate within their, that is usually associated to them. But we will leave it for that for a second. Then let's close the figure window. I think there was one Slido question whether I can scroll up and show this sign plot again. If this was referring whether you want to note that down for later reference, then you could also access the slides. Basically, maybe I can show that to you real quick. Oh no, it's not prepared. 1 second. Okay, this is a little too far. Maybe it's 95 something there. No, it's not. And basically, you have essentially screenshots of what we did so far. So, for instance, with the sign plot, if you just want to redo that, have a minimal working example to get that up. Okay, great. Let's return and go on with next thing. Maybe we might be interested in putting our parties into a pie chart, and that's also rather forward. So here we do plt.pie, but we have to be a little bit careful because here the interface is again a little bit different. So here we have an x equals results and a labels equals parties. And the reason plt.py or some plots have different interfaces is that often these functionalities have been added at different times to the Matplotlib library. And so they might not be too consistent, although for the plt.py, it kind of makes sense to have it this other way around. Either way, let's just look at the plot. And then here we get a pie chart. I mean, something you could also do with Excel, but here you can also do it with Matplotlib. Okay, and in general, if you want to do certain plots, I would just advise you, there's a good, I will also show you the link later on, there's a good collection of examples that Matplotlib provides, which you can use in order to build the plots just based on these examples. And then you also see how the interface works. And if you use these calls a couple of times, then you get accustomed to the interface. Okay, let's close that. And let's ignore the parties for a second and move on with a scatter plot. So a scatter plot is basically that we have some coordinates, let's say in 2 dimensions, and we just want to create dots there. This can, for instance, be used in order to analyze some data and then see what you can find of kind of a relationship within this data. And here I want to use normally distributed values. So let us start by drawing some normal distributed values by doing, maybe let's call it standard normal data, and do a numpy.random.randn for normally distributed random values. And I want to draw them in a 500 by 2 shape. And this basically means we draw it in, I mean, we've seen that yesterday, we draw 500. So we have basically a matrix with 2 columns and 500 rows, and we draw normally distributed random values. We can also take a look at that and see it like that. And the reason I did that is also to introduce you to a convention that's often used in Python, and in particular with respect to Scikit-learn. Other libraries might do it differently, in that when we have a data for which we have a certain number of samples and a certain number of feature dimensions, and usually this is so-called tabular data, we arrange them in a way that the rows indicate the number of samples and the columns indicate the number of features. So for instance, if you perform measurements in let's say in real life, and your measurements consist, for instance, of a temperature sensor, a pressure sensor, a force sensor, and something else, then pressure, temperature, and force might be are your feature dimensions. And then if you perform multiple measurements, those go into the rows. And translating that into this standard normal that we have here, by looking at the shape, we see we have 500 samples and 2 feature dimensions. And now I want to create a scatter plot where we have kind of a 2-dimensional plot in which we see these 2 feature dimensions. Let's use plt.scatter. And the scatter takes 2 arguments. So we need an array of coordinates in X direction and an array of coordinates in Y direction. So we will take our standard normal data and we have to access the entirety of the first column. How do we do that? So we use the slicing operation, not slicing, but the fancy indexing operations that we've seen in yesterday. So we will extract all the columns and then the first row. No, we of course have to use a 0-based indexing, so it will be 0. And then we have standard normal data, all rows, but first column, so the second column in a 1-based indexing. And then we can create the scatter plot and show it. And then basically we get our plot here. We decided to ditch the interactive Python session, at least for the parts where we want to use plots, which are going to be most of the parts from now on. So we have to resort to something where apparently the screen sharing works. So it must be some really inherent issue. Maybe I can fix it in a lunch break and then we can go back to the interactive sessions afterwards. But until then, I would use Jupyter notebooks. And I'll also quickly show you why that is the solution. Maybe you also will prefer that. Okay, so I will close this interactive session and go out. And then I will just create an Jupyter notebook. So maybe let's close what we have here. So I will create a new file here and call it maybe Matplotlib examples.ipynb for interactive Python notebook. We've seen that yesterday that if you have the Jupyter notebook extension installed, this should directly open something within VS Code. I hope that works for everyone. The reason we are using the Jupyter notebook now is that there's this fancy functionality that if you do plots, they can be presented inline. That's also what I mentioned yesterday, that these Jupyter notebooks are a collection of code, description, including potentially also LaTeX formulas and plots. So for this, let's now focus on the notebook. So I will close the file explorer and then minimize the terminal down here. And then we are back in these cell structures. Then first, of course, we need our imports again. So I will do import numpy as np, import numpy as np, and then import matplotlib. And here again, if you want to use the auto completion, this is now quite similar to when you would how you would write a script, in that you have to use the control space, so strg plus Leerzeichen in German, in order to get an recommendation for auto completion. And then we need to import matplotlib.pyplot as plt. And then with a shift enter, you can execute the line. And you first have to, at least in my case, I always have to select a kernel prior, and I will use the Python course environment. So click select kernel and then Python course environment. And then you should be able to shift enter and execute it. And you also see some nice progress indicator, and also told you how long it took to execute that particular cell. And let's just, as a proof that it works, let's first have the sign plot again. So we have to create our table of values. So with X, we use numpy linspace, from 0 to 1, and also used it from 0 to 1 with 100 points. And then y we introduced as numpy.syn of x in order to have the vectorized application of the sign. And then in essence, if we do a plt.plot x, y in here, we should see the plot. Well, of course, not until 1, but until 2 times numpy.py, and then we get our sign. So it's a little large font here, but you should be able to see that. And here we also don't need a plt.show, since kind of this is some kind of, let's say, a magic in between these Jupyter notebooks that it highlights them in place. And if you were to save these Jupyter notebooks, so for instance with Control S to get rid of the dot down up here, Control S, and then save the file, the saved file would also include the plot here. And let's just continue on with the scatter plot again. So we kind of created this standard normal data by drawing random numbers, rand n. And you see kind of these pop-up windows are super large. They shouldn't be that large on your machine. It's just because I increased the font size here such that you can see it easily. And then draw 500 by 2. And again, remember, this was to match the tabular data where we have 500 samples and 2 feature dimensions. And this was the X and Y. There's a question on Slido. Is there a way to export the plots, for examples, as PDF or PNG files? Yes, there is. So I think in the Jupyter notebook, it's quite easy. So you should be able to, oh, I think maybe not. I'm mistaking that. Worst case, there's always, so this is kind of the way how Matplotlib decided to implement this, at least in this PLT simple interface that we are using here, that we kind of have a state machine, meaning that the plots are kind of implicitly referred to in the background. One could make them a little bit more explicit. We won't be doing that here because later on I want to introduce Plotly to you, which I believe is a little bit more of the future-proof and feature-extended version of doing plotting in Python. Therefore, I don't want to go into too much detail with Matplotlib. But to save a plot, you do plt.savefig in order to save the figure, and then provide it with a path to save it. And then, for instance, example plot saved. And then based on the extension that you give to the file, you can either save it as a PNG or PDF. I think PDF should also work. And then with Shift Enter, if you execute that and look at your file explorer, you have an example plot saved. And the nice thing about Visual Studio Code is that you can then also preview the file here, although it's not that nicely formatted. That's because we did the plotting within Jupyter notebooks. If you would do this savefig from a script, also from the interactive Python shell, then it probably would have used different stylings. So such that it doesn't have like this transparent background. I hope that answers the question. Let's continue to the scatter plot. Then let's do the scatter plot. So plt.scatter, and then scatter our normal data by, let me close the file explorer here, by doing, I hope it's okay if I zoom out one level because it's really cluttering for me. Then we use our standard normal data and access all rows and the 0th column. So :0, and then standard normal data :1. And then if we Shift Enter, we get our scatter plot. We can also modify it a bit, for instance, by adding a grid by using plt.grid. And then, we're getting a grid to it. And you see, again, like with the number, what I said yesterday, the number indicates the order of execution in the Jupyter notebooks. And here we executed it a couple of times. If I were to re-execute it, it would get number 10. And now what I want to do is kind of a little bit of mathematics in order to also go back to the NumPy introduction that we had yesterday, because in order to transform a multivariate normal distribution into a custom covariance and custom mean vector, we can make a so-called affine transformation. I will just quickly show this to you on the slides. So someone was asking, is there a way to assign a plot to a specific variable and then reuse it later on for axis rescaling, naming the axis, or only the one in the memory? There is a way. And I wanted to avoid that kind of interface because I personally, for me, it's kind of, I use Matplotlib for quick and dirty plots. So when I just want to have something that works out of the box and is super fast. But whenever I try to do something more advanced, I personally resort to Plotly because it just has way more customizability. And on top of that, especially if you want to do three-dimensional plots or plots with a lot of data in it, Matplotlib tends to slow down. It, of course, depends on the backend. So this backend is the one that we try to adapt in the break, but didn't turn out to work. But so bottom line is there is a way. It is by explicitly instantiating figures and then adding axes to these figures. And the reason I don't want to show it here, it is just because it's my personal flavor of using it. So I hope that answers the question in this way. So I would take it answer. Feel free to answer. Feel free to ask a follow-up question if that was not a sufficient answer. Okay, let's go to the slide. So basically what we have here is a scatter plot. And I now want to kind of move the scatter plot somewhere around. And the idea is that if you have a multivariate normal distribution, in case you've heard that before, and we've seen that with the blue dots here, that was our first scatter plots, we have kind of these, you could, if you draw density lines out of this, you get this rotation, circular shapes, and they are centered at the origin. So at 0, maybe a different color would be better suited here, but at 0, 0. However, we can also transform that into arbitrary normal distributions. So if we draw the data that the way we drew it, we draw it from a standard multivariate normal distribution centered at the origin with an identity covariance matrix. But we can also transform it into arbitrary mean with arbitrary covariance matrix. And that's kind of highlighted here with the orange dots and the centering. So if you approximate center, it's roughly at 2 and 3 maybe. Oh yeah, actually that's where I want to go. So good indicator here. And then the density lines are also no longer, how you say, it's like circles, but rather they are ellipses that are also rotated. So in that case, maybe you would draw something like that. So that's kind of the density line that you find here. And we can express that by this particular covariance matrix. And in order to make the transformation into these arbitrary points, we need to perform a matrix decomposition. And the reason I'm doing that is probably rather a little advanced example in order to highlight again that we can do all of that with NumPy. So we need to take our covariance matrix and decompose it into its Cholesky factors. This is basically just taking the square root of a matrix. And then we have to do this affine transformation. And affine is just mathematical for multiply a matrix with something and add a vector. So we have the L matrix that we got from the Cholesky decomposition, and we add the mu vector. And this kind of shows us a lot of things that we learned yesterday with NumPy. So let's just do that. For this, let's head over to VS Code again and define the mu vector where we want to be as NumPy array of 2 and 3, and then Shift Enter to execute. And then let's define the covariance matrix as NumPy array. And then in the first line, we want to have 2 and 0.7. And in the second line, 0.7 and 1. If you've never seen that before, you can interpret the covariance matrix in a way that the diagonal elements, they express how much the scatter points are like stretched in X direction, or like in this particular direction. And the off-diagonal elements define so-called covariances that define, in essence, how much it is rotated. And we can take a look at the covariance matrix, and we see this is our 2 by 2. So 2 axes and 2 dimensions in each axis, 2 by 2. And we want to compute the Cholesky factor out of that. And usually this Cholesky factor is called L because it is a lower triangular matrix. And we get L by calling numpy.linalg.Cholesky. And again, if this really sounds like you've never seen that before, it's again just an indicator that we have this kind of algorithm. So we don't have to worry how, for instance, to do a Cholesky decomposition. But here we will just hit use NumPy and then obtain our L factor. You can take a look at that and see it's a lower triangular matrix. So it has zero values above the main diagonal. And then we can do our affine transformation. So in essence, if we want to do the affine transformation, we have to matrix multiply 1 point with L and then add the mu vector. So for instance, if we take one data point, and remember, we have this tabular structure where we have the number of rows which indicate the samples. So basically each scatter dot has a row. And then in the columns, we have the feature dimensions, so 2 dimensions. And if we want to extract one arbitrary data point, let's take the 0th, aka first one, by doing standard, normal, and theta, and then extract the 0th row and all the entries. So basically, we will slice out the very first vector. And this should be a 2-dimensional array. You can check that. One data point dot shape. And here you also see one property of the Jupyter notebooks is that if you just execute a command, or basically a bunch of commands, the very last command, if it is something that can be printed out, will be printed out such that you can inspect the variables. That's why I'm using a new line or a new cell for each execution here. So maybe just a quick recap. So we defined the covariance matrix, which is our array matrix. And then we used an algorithm, which is the Cholesky decomposition on this covariance matrix. And this basically gave us the square root in quotation marks of the matrix. And we can use this in order to transform our standard multivariate normal data into this special multivariate normal data. Okay, now that we have our one data point, we can transform this one data point. And I'll call this one data point transformed and say, well, one data point transformed is going to be mu plus L times one data point. And then think, yeah, that's how I would do it in MATLAB, because in MATLAB, the asterisk indicates matrix multiplication, but here in NumPy, we have to resort to add, since add is matrix multiplication, because by default, it would do an element-wise multiplication. And maybe sometimes these element-wise multiplication, they will work, but that is because the NumPy attempts and broadcasting in some sense. And of course, sometimes a broadcasting can fail if there is no suitable auto broadcasting rule. Okay, this is one data point. And this should, give us one data point transformed. We can look at the one data point, and you also see it's moved. It moved, and it probably also would indicate when we have a couple of them that they are rotated. But now you might say, okay, fine, Felix. Now we have the one data point transformed, and we have 500 more left. Should we now use a loop? I mean, I told you earlier that you should avoid loops as good as possible. So we have to kind of rethink a little bit. And for this, let me return to the slides again and put an emphasis on how we could reformulate that. And let's go to the slides. And let me get my drawing tablet here. I think I can put it to the right here of this plot. And the idea is, I mean, you already see the solution in here, but I just wanted to show this to you. If we take the matrix X and have the matrix X as our 500 by 2 matrix, then we have the dimensions in here. So the 2 dimensions basically. And what we want to do is we want to multiply or matrix multiply each row with this matrix. And what we could do is we could take out these vectors, or we consider these vectors here, and perform a matrix multiplication from the left with this with our 2x2 Cholesky factor. So basically what we have is we could extract this row, and this would kind of give us a row vector here. So an 2x1. And if we make a 2x1, so basically this would be our 0th sample transpose. And if we make a left multiply with the transpose L, so this is L, our Cholesky factor, which is 2x2. And if we transpose that, we get another vector. So we get another vector. So maybe this is then the x tilde vector. And just by the rules of matrix multiplication, it will also be a row vector. And it will be something like this, 2, 1. And so we could transpose it, right, in order to get back to our column vector. And the essence is that if we want to have it in that format in the long term, so in the long term, we also want to have, long term, this is kind of the goal here, we want to have an x tilde matrix, which contains the transformed entries. So we have 500 entries, and in each row, we have the transformed vector. So what we can do is we can make a matrix multiplication of this 500 by 2 matrix with the Cholesky factor from the left, but transposed. And then we get our x tilde. At least then we have performed the Cholesky factor times vector, but then we still have to add our mu matrix. And as you can see here, that works flawlessly. And that is because there is this idea of auto-broadcasting, such that NumPy in that particular case understands that we would want to add the mu to each row. So this operation in that sense will be well defined. Okay, this might sound a little bit advanced now, but in the end, what the reason is why we're doing this is to avoid the for loop. So we avoid the loop over the 500 elements. We could implement that, and probably at that problem size, it might still run sufficiently fast. However, just to make you aware of how you can reformulate your problems into a way to take advantage of the faster operations in NumPy. Okay, long story short, let's just implement it. And so essentially what I have here, let's implement that. So let's go over to VS Code again and say, how should we call it? Maybe let's call it custom normal data is going to be mu plus standard normal data matrix multiplied with L.transpose. And if we then look at this custom normal data, you see that, well, it's a long array. Maybe I shouldn't have printed it. You can suppress, oh, by the way, this you can suppress the printing with a semicolon here. So essentially, we now have our transform data, and let's just plot it. So plt.scatter and see custom normal data, all rows 0th column, custom normal data, all row 1st column. And now it is kind of, well, we don't see much, so maybe it might be reasonable to plot both into the same window, basically. So let's do plt.scatter, standard normal data, that way standard normal data :1, and then plt.scatter custom normal data :0 and custom normal data :1. I hope this is clearly visible on the screencast. And maybe let's also activate the crit, because why not? And let's just run it. And here we now see something of course, not identical to what we had in the slides, since it's pseudo-random numbers, and therefore they can differ since we haven't fixed the random seed. But in that particular case, we see that we have changed the data from the standard normal distribution into one where we have a different mu, so a different center, as well as a different covariance matrix. And as said, if we save the IPython notebook, then those plots will also be stored, and we can use them, or maybe we can share them if we, for instance, host the IPython notebook on Binder or some other servers, or just on GitHub, or I think GitLab also allows that. So if you prefer GitLab over GitHub, or if a custom GitLab instance, then other people can see that and we can share ideas or data analysis based on that. So I will quickly save that with Control S. And maybe in case it was a little bit too quick, let me just show you the operation once again. So we have the standard normal data. So this was our 500 by 2 matrix or array, basically. And then if we have a matrix multiplication with the Cholesky factor transposed from the right, then this basically mimics as if we were to do the for loop over all the matrix multiplication or the matrix vector multiplications. And then we used an idea in NumPy that's called auto-broadcasting, because remember, broadcasting yesterday was the requisites for broadcasting were that the arrays to be broadcasted have the same number of axes, and the mu vector is just an one-axis array with 2 dimensions, whereas the result of this matrix multiplication will be a 500 by 2 array. And then NumPy knows if the arrays match in the last axis. So the mu has 2, so it has only one axis, but it is 2. And this one has 502, but it also has 2. And then NumPy knows that it has to do a broadcasting over this first axis. So it kind of interprets this first axis as a batch axis in that sense. And batch axis refers to if you do something in batch, you do this over and over again. And again, the crucial point is NumPy does the for loop for us, and we don't do the for loop, which is getting us to acceptable speeds in larger data sets. Okay, great. I hope that cleared things. I hope you could follow along, and let me return to the slides to finish off with the Matplotlib section. Okay, so I also noted that here. Have you seen the auto broadcasting when adding new? Okay, great. Then there's one more thing I unfortunately cannot show to you because the IPython notebooks don't seem, at least the plots don't seem to screen share. But if you call plt.ion in your IPython shell, you turn on the interactive mode. And I think that this is quite close to what Matplotlib does with its plots. So you instantly get a plot and it instantly updates. So for instance, if you add a new plot, then you see it. I mean, you would have saw it, I would have shown it to you then. And also if you make interactive edits to the plots, like add labels, it will instantly update. And I really like this on mode, especially for large, small to medium-sized data visualizations, because I also personally like to work off this IPython notebook. But of course, if that could not convince you, and now the session with the Jupyter notebooks was kind of the preferred way for you, then of course, feel free to use that. And certainly, of course, this ion mode does not work if you execute it from the script. I mean, it does not work, but it's not giving you any benefit there. Okay. Then we've seen that. I mean, I would have shown it to you anyways with the Jupyter notebooks, but now you've seen it that it also works. We would have looked at some data of the Apple stock, but I think we can also do that in the example with Scikit-learn later. And then I just want to leave that here for reference because I told you multiple times, I tend to forget a lot of things about the interface to some libraries, and especially also how you name certain things in a figure. I'm really bad at remembering this. As a couple of things I do because I use them frequently, but others I always have to look it up. And say, for instance, here I took an example from the Matplotlib website, and it's just that there are like conventions on how certain things are named. But I think you will get used to that over time. It might be interesting to take a look at that, just that you kind of orient yourself. And then I just want to highlight subplots, since this is also something that people are interested in. And there are multiple interfaces on how to do subplots. Since my personal relation to Matplotlib is to only have it for quick and dirty plots, I also prefer to have the quick and dirty way of plotting here. And there is a call to, it's called subplot, and it takes a number which can be decoded as, so it has basically 1 to 1, for instance, which means, I always forget that this means the number of rows, the number of columns, and this means the index. And the weird thing here is that the index starts at 1. So this is super inconsistent with Python convention, but I think it's supposed to match how MATLAB does it with the subplots. So here in that case, I would have shown you a subplot or a plot with 2 subplots that are horizontally next to each other, basically. So we have 2 columns. And yeah, this is something you could look into if this is something you need, but I'm pretty sure you can catch up on that in case you require that. Okay, and we have also looked a little bit at the documentation. So here I have the website of Matplotlib. Sometimes the websites are a little better formatted than when looking at the help command in the terminal. And usually they also give nice examples on how you can use that. Although personally, I would prefer to always look at example libraries, so not libraries, example galleries, where people created plots from different kind of data. And based on that, you can then maybe take the best of those examples. I mean, probably you've worked with examples before. So then you can avoid a little bit the confusing documentation from time to time, although it's very vast documentation. Okay, then as in every section so far, let's talk about what we did not cover. So first of all, we did not do any plotting in 3D. So we will do this with Plotly, since I said I like Plotly a lot, but maybe I can convince you with that. Oh, sorry. And then we do not do any image plots, heat maps, histograms, streamline plots. Streamline plots are quite cool. So stream plots are like if you have vector fields and you can then create streamlines. It's quite cool that Matplotlib does that kind of like out of the box. It's nice. There are also options for interactivity, especially if you want to have, for instance, sliders that change change how, for instance, plots are displayed or change certain data sets. The reason I'm not including this in here, because as mentioned earlier, I really like the Streamlit library. I will show to you later. And this kind of, at least in my perspective, allows for really nice interactive visualizations that are also way more intuitive to write than using the interactivity of Matplotlib. But of course, that's a little bit opinionated. Maybe you prefer the way Matplotlib does it. So it's just there. And of course, you can look that up. And then, as mentioned, there are also some other APIs. So Matplotlib has multiple hierarchies of interfaces. So I've shown you probably the most simple interface to Matplotlib. But of course, there are other ways to interface in case you need that. And as mentioned here, these are some example plots where you can copycat certain concepts and adapt it to your particular needs. Okay, that's basically the end of the Matplotlib section. Okay, let's continue with Pandas. So this is kind of a chapter on now some advanced plotting concepts and some data science concepts. I mean, data science in quotation marks, we won't go too deep here though. And it's kind of like this, at least last year when I prepared the workshop, and I don't think it has changed much since, that whenever you think about data science, so data science, I mean, probably I don't have a good definition for this, but data science is kind of the idea of working with data, usually large data sets, and extract meaning from that. And this has multiple applications. I mean, probably originally that kind of comes from business applications where you gather data from sales or in different ways, and you want to make informed management decisions on what would be the right thing to do next. And over the last years, this has come to be associated with Python. And it's the same as with scientific computing. It is not associated with Python in the original sense, but it is associated with the ecosystem of Python, so the libraries. And one particular example for this is Pandas that we will look at. And here I had some nice thoughts. So working with data becomes more and more prevalent. I mean, this is kind of a no-brainer. What I believe though, and that's probably more relevant for this workshop, is that in science and engineering, there will be kind of a hybrid between data science and machine learning and physical models. What this means is you often, like historically, many things that happened in scientific computing are based on models that taken from physical hypotheses or like physical laws or axioms or however you want to call them. Like for instance, if you are into like structural simulation on Cauchy's laws of motion, then you have, for instance, the Navier-Stokes equations and so on. My particular belief is that the aspects of data science and machine learning will try to bring up like hybrid ideas between these physical models and data-infused aspects. Of course, it's kind of a controversial thing, and you also see people saying that many things that are done towards the machine learning research in those physical sciences is not that well-grounded compared to physical models, and probably some concerns are quite valid, but there's still a lot of potential, and I think it's still it's kind of helpful to be aware of that potential, although you might not use it that much for yourself. And this new field is also sometimes called scientific machine learning. I mean, it's actually not a new name. This name exists a couple of decades now. And the reason why I believe Python is a great language for this is, as mentioned, it has this data handling tools that we will see now. We have the machine learning aspects that we will see tomorrow. And we have the scientific computing aspects that we've seen hopefully already with NumPy, and we'll also see later when we look at SciPy. And as I mentioned a couple of times, this makes Python kind of a glue language. So it is not Python itself that is the language for data science, machine learning, scientific computing. It is the ease of use and the ecosystem that makes Python so great. And that it's free. That's on top. I think this is probably motivating the other aspects. Okay, let's start into Pandas and let's look at things a little bit more in more concrete terms. Just this is to give you a little bit of the big picture. And I want to look into data frames. So data frames is the essential concept that Pandas brings up. So it's the same like with NumPy, brings up NumPy arrays. Pandas is associated with data frames. And the easiest thing to understand what data frames are is basically you take an Excel table and make it available in Python. And we will look at the following example. So we've already looked at the results from the election in 2017, Bundestag. And here I've just extracted some data, and we have the party and the results from the election. We just many seats they got, their chairman, and a particular legislative decision. So I don't know how familiar you are with that, but some of the legislative decisions that are made in the federal parliament are publicly available, where you can see which party voted for which, and I think you can even see who voted for which. Some are anonymous though. And here we have a decision on the budget for 2020. I mean, it's like an example I brought up, and we want to use that in order to assess some essential aspects of Pandas. And what I want to emphasize here, why I have the screenshot, is that there is a difference to a NumPy array, because when you have this two-dimensional data as a table, you can also think of it as a two-dimensional array. Although one of the big differences the Pandas data frame allow us is to have different data types per axis. So this per column. So different D types. And if you look at that, then you have, for instance, here maybe a string, then you have a float, and that's an int, that's a string again, maybe that's an int, and that's an int, that's an int, and so on and so forth. And that's kind of what you need when you work with these data sets. And Pandas has the functionality for this, or maybe also hides away the complexity behind that. Okay, long story short, let's just create a Pandas data frame. For this, let's go over to VS Code and code it down. So I will open Visual Studio Code. And since we will be plotting again later, we will stick with a Jupyter notebook. And for this, I will open a new one. So go to the File Explorer. And let's do the pandas example.ipynb. pandas, or give it a different name if you like. And again, if you have the correct suffix, then VS Code will identify that. It will also give you the corresponding icon to the left, and then we can open it and get a new Jupyter notebook. Let's close the File Explorer and then select the kernel. We want the Python course kernel, or the kernel you want to use. So for the first example, I don't want to work with the Bundestag election results yet. I just want to create some artificial data frame so that you are familiar with the creation routines and how to access that. Okay, for this, let's first import pandas. So import pandas. And as mentioned, all these packages are usually having abbreviations that are common, and the common abbreviation for pandas is PD. Shift Enter for execution of the cell, and then let's create an example data frame. So I want to call this an example df for an example data frame. And for this, we will do pd.dataframe and then opening, closing brackets. And from time to time, it might seem a little bit novice, the things we do. And that's because yesterday we kind of skipped over this object-oriented or class programming part of Python. And essentially what we're doing here is we are accessing, first of all, the namespace of pandas. And then there is an object or a class. And also, if you highlight over it, I get the, how you say, the documentation is telling me that's a class. And we can use an opening and a closing bracket in order to instantiate a class. This will call the constructor, if you've heard that before. But if you haven't heard that before, it is just like creating a new object for us. This is similar as if we were to do a equals 4, then we would instantiate a as an integer and assign it the value 4. And here we want to instantiate a data frame and assign it to the variable an example data frame. Okay, Shift Enter will execute. And then we can maybe print it out to see what it tells us. And yeah, okay, this is because it uses a different formatting in the, maybe if I use print, does that work? Is that the formatting? Yeah. So if I print it out, that's similar what I would have seen in an IPython shell. It tells me it's an empty data frame. Yeah, well, we don't have any data. What data should be in there? And it consists of columns and indices or index. And so let's fill that. And for the sake of argument, we kind of can think of a data frame as a hybrid between a NumPy array and a dictionary. A dictionary, if you remember, this was where we could use, for instance, strings as keys in order to index certain aspects of the dictionary. And here we want to fill the data frame with new information. And let's just fill it with an excerpt of information from this Bundestag example. So let's say an example data frame exists at party. So this will create a column called party. And then we want to fill it with the data, first of all, with CDU, CSU, and then SPD. SPD, sorry. I tend to like pronounce it German, but yeah. So this is basically what it is doing. It is creating a column, and it is similar to a dictionary. If this column does not exist, it will create it for us. And if it would exist, then it would override the data that is in there. And then we want to fill it with a list with these two entries. And let's just execute that and then look at an example data frame again. We see, okay, that's just the way it is printed here, but it kind of is shown as the table where we have row 0, row 1, again, 0-based indexing, and then we have the party that is involved in here. And then let's just add another column by saying an example data frame, and then result is, and here we have 33.1 and 20.5. Shift Enter and show it. And then we see, well, we have a new column in our data set. We have the party, we have the result. And so we have kind of an extraction from our database that we want to read in later on. Okay, and then the aforementioned point was that each column has its own data type. And we can access this, for instance, by saying an example data frame dot dtypes. And this will give us the dtypes, and we see, well, party, it's an object, and result is float64. Object is kind of a more general way that can contain multiple different data types. More precisely would be to have it as a string though, but in our particular case, that does not greatly matter. Okay, that's basically about the data frame, how you can create one yourself, but this would of course be tedious to fill it that way. So we want to interface with what we have on our in our data folder. So let's open up the file explorer here, and under the data folder, we have the 19th Bundestag example, and I have it in two different data formats. I have it as a CSV file and as an ODS file. So in case you haven't seen that before, ODS stands for Open Document Standard. That's kind of the Excel variant of, the LibreOffice variant of Excel. And the reason I put that in here, I want to show you that you can read from Excel files or LibreOffice way Excel files as well. And Pandas has a lot of read-in routines. So I want to say data frame from Excel is going to be PD for Pandas. And then if you just type out read, you get many options: read CSV, read clipboard, read Excel, read Feather. I don't know what Feather is, but I mean, you get the point. Read JSON, read HTML, and read SQL as well. So there's a couple of options of what you can do with Pandas. I mean, a lot of options, covering probably most of the widely used data formats. And we want to start with reading from Excel. So let's do pdf.pd.read Excel, and then opening and closing quotation mark, and then with putting in data, it also gives us an auto completion for the file path. And then I want to have 19th Bundestag example.ods. Sorry, no, I did the data twice. That should work. And with a shift enter, we can execute that. And I'm pretty sure you should get an error. At least last time, we should be getting an error. It should say something to you. Well, you need to install this and this library in order to perform the read Excel. So you can install the library, but I mean, this is just like for showing that it could potentially work that you read in from Excel. We will now resort to the CSV file, which Pandas can load on without any problems. So let's do df from CSV, data frame from CSV, pd.read CSV, and then we do 19th Bundestag. It doesn't work like that. That's weird. So data 19th. Okay, let's write it out. 19th Bundestag example.csv. Shift enter, and that should work. It should not raise any errors. And then we have df from CSV, and that is basically the one that you have seen before. By the way, fun fact, the chairman kind of give the indication. So this is actually, sometimes they have like a double chairman, but I always took the first name of the chairman. And then it kind of turns out that all parties or all fractions in the Bundestag only have male chairman. Quite an interesting observation, at least in this 27 election. I don't know whether this has changed. Okay, so we have this df from CSV. Let's just rename it and call it Bundestag. Why not? And say Bundestag is df from CSV. And then we want to do something with that. So what are some basic usages that you could be interested in working with data frames? So first of all, you could be interested in extracting some data. So maybe saying Bundestag and then give me all the parties. So I want to access column party. So Bundestag party, and then, well, we get this party column. But maybe you say, okay, well, I'm not just only interested in the party. I also want to know how the result was and how many seats they occupied in this legislative period. so seats and seats in the parliament, and then do Bundestag. And then basically we want to access at multiple columns at the same time. And if you remember, when we want to have a collection of variables in Python, this refers to a list. So we have to do the square brackets for an indexing. And then we have the angular brackets, again, in order to indicate a list, and do, let me see, party, and then results and seats. I hope that was correct. No, it's result, sorry. And then like this, and then we kind of get a sub view on this data frame. There's a question on Slido saying the budget 22 voting sum does not add up to match the number of seats for some parties. Why? Yeah, good point. Why? Let me see. I mean, this is something that I wanted to check with you anyways. So yeah, you took the example. Well, that's a good point. Why do they have like more votes here? Yeah, I see your suspicion. Yeah, could be that I made a mistake when copying the data set. I don't want to like introduce this to be. Could be that I made a mistake. Could also be something else. Maybe this was the number of seats they were allocated right after the election, and this changed for some strange reason. But I don't think that should be too relevant for our discussion here. Okay, this is one of the indexing that you could be interested in, but you could also be interested in, for instance, indexing by the row index. So for instance, you want to extract the data for one particular party, let's say, for instance, for FDP, then you might be interested in extracting the third row. And if you were to try to index the data frame in a way you would index an NumPy array, you would run into trouble because that should not work. So we can try, for instance, say you want to have the third row, so from a zero-based indexing, and then all columns, and it says, oh no, this does not work. And the reason is Pandas data frames use this kind of column preferred indexing. So in order to have an indexing that is have an indexing that represents the Pandas data frame as a NumPy array of a kind, you have to add the .ilog. So Bundestag.ilog for, I think, index location. I think that's probably how you would spell that out. And if you then apply that, you will get the row entry, and you have the corresponding row with the name to it. And there are, of course, many other fancy indexing. As said earlier, a lot of these indexings might come up in particular use cases. And there are often many ways to get things done in Pandas. And sometimes it might not be the most elegant way. You might not find the most elegant way, but at least in the beginning, it is helpful to just get it done. And therefore, it might also not be too bad to have something that is a little bit ugly in the beginning. So much about indexing. Let's just look at some operations you can do with this Bundestag dataset. And for this, we want to, for instance, sum up. So do something that, as the question of Slido probably indirectly already did, to kind of check for sanity in our data. Whether the data that we have is matching what we would expect for the data. And for this, I want to check whether the results and seeds add up to the value that we expect them to have. So I want to extract these two columns, and then I want to sum over the rows. And this can be done in the following way by saying Bundestag, and then we use an indexing with a list to index two columns at the same time, and to have result and seeds. And then I want to take the sum in order to sum them up. And what this does is basically it sums over the rows. So it's not like with NumPy that we have to identify the axis over which we want to sum, but rather here it kind of knows the structure that we have this tabular data. So Shift Enter, and then we see the result. So the percentage result of votes adds up to 100%. That's kind of how it should be. And the seats add up to 709, which is actually not what they should be. Of course, it's a little bit too detailed, but the design capacity of a Bundestag is actually 598 seats. Fun fact, I mean, probably some of you know that. So that kind of exceeds that by a large number. And there are some really strange rules I have never fully understood, but how parties tend to get more seats than they have been allotted based on the results. It's because of the rather complicated voting mechanisms. So that's in that case not an indicator for an error in the data set. Although, of course, what was mentioned earlier, that this does not add up, is for me probably more an indicator that I'm certain I made a mistake here. But it's good that this was that you figured that out. Either way, so this is kind of a sanity check on the data. And these sum operations, I mean, yesterday we called them reduction operations because they take away an axis from our data. And there are like other operations as well. I mean, of course, we can ask ourselves what is like the meaning behind that, but we can also, of course, take the mean. Sorry, oh, this does not work. Let's just do it verbose. Bundestag result seats, and then dot mean. And then we see the mean result is 40.3%, and the average number of seats are 101. How about the standard deviation? Bundestag result seats dot std. And here we go. I mean, of course, the interpretation of these results are rather questionable, but we see we have a high variation in number of seats. And that, of course, makes sense because we have a couple of large parties and then a handful of smaller parties and so on and so forth. Another common use case for Pandas data frames is to do an indexing based on the condition. So let's say, for instance, you want to have the, you want to, for instance, access all the parties which had a voting result that was better than 10%. So by looking at the data, since it's sorted as well, we kind of know this must be the first four parties. But let's just do this a little bit more programmatically and find them by a condition-based indexing. So for this, we can say Bundestag, so access the Bundestag or the Bundestag data frame at the condition where Bundestag.result is greater than 10. So check where at which rows the Bundestag column result is greater than 10%, and then access the Bundestag data frame at this particular point. And this should result in the first four rows. And if we look at this condition in more detail, so if we, for instance, perform this operation outside of the indexing and say Bundestag.result is greater than 10, then this kind of returns a Boolean array or a Boolean data series in that case. And it says true, 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 false, 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 false. And that's, of course, because it is kind of like a vectorized application of the comparison operator in that case. So for the first four entries, this condition indeed holds to true, whereas for the last three entries, it holds to false. In that particular case, Pandas then knows how to use these kind of data series with Boolean entries as an indexing. So it basically interprets that in a way that, so if we have a true, we want that data entry, and if we have a false, we don't want that data entry. And let's just, let's chain some operations here. So for this, I want to check where the Bundestag result is greater than 10%, but the party has received less than 100 seats. So for this, I want to do Bundestag opening and closing square brackets, and then opening and closing regular brackets to check whether the Bundestag result is greater than 10 and the Bundestag result, seats is smaller than 100. And this should yield AfD and FDP. And this might now seem a little bit to why do we need it in this particular way? So first of all, we can't use this AND syntax. So we have probably seen that yesterday that Python is kind of like this verbose, really verbose language that we can use English language in order to express operations. At least I think this should not work. Yes, it does not work. Exactly. Sorry, I will go back to the ampersand. And the reason we have to use the @ sign here is because we have to do an vectorized version of AND. And the AND keyword, so the English AND keyword, not the ampersand, is a way in Python to do like scalar-based condition checking. So if we have, for instance, true and false refer to false, of course. But here, as said, if we check for a condition, we get an array of booleans. And here, if we check for this, we get another array of booleans. And here, in that case, this would return to false, false, true, 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 true. And then we have to do the element-wise comparison. And this is done by the ampersand operator, because this one vectorizes properly. And then we have to account for the order of execution. And in that particular case, the comparison has to be set in brackets in order to match the control flow, so that we first perform the comparison operation, and then we first perform the comparison operation, and then perform the ampersand, the vectorized AND version. So we stopped before the break where we looked at some conditional indexing for Pandas data frames. And now I want to show you some functionality for Pandas, basically where you can directly plot out of Pandas, which is some convenience function. And then we will look at some examples together with Seaborn and Matplotlib, also in conjunction with Pandas. Okay, so for this, let us now ignore the Bundestag data frame for a second and not the Bundestag. Of course, we will keep the Bundestag example. I'm sorry, I was wrong. Okay, so I want to plot. So earlier we did a pie plot, if you remember, where we had the issues with the screencast. And I want to show you that you can directly do the plotting out of Pandas, which is, of course, an extremely nice shortcut. And for this, you can do bundestag.plot, which kind of opens the plot options that are associated with a Pandas data frame. And in that particular case, you can, for instance, do a pie plot, and then you just have to indicate over which axis you want to do a pie plot. And so, for instance, we want to have the axis being the results here, or maybe what should we choose, or maybe the seeds. Then let's have y equals the seeds. And hopefully this works. Yes, nice, that works. Okay, here we go. Okay, that's not how I was supposed to, what I wanted to have it here. Yeah, okay, I see. So here we kind of have this plotted over the number of seeds, and we've chosen the y-axis. So here the axis which refers to the pi entries or the pi chunks. And then it was associating the indices 0, 1, 2, 3, and so on to that. That's of course not directly clear. I mean, we can associate which party must be which just based on the proportion. However, or basically the reason why it chooses that is that the Bundestag data frame consists of an index column, which has this 0, 1, 2, 3. And this index column is then basically what the pie plot or the plotting for the data frames is using as the naming for the chunks in this pie chart. However, we can also change that in that we can make the party be the indexing column, which would also be a reasonable thing to do. And for this, there are multiple ways. Let's just reload the data frame into the IPython notebook. Let's continue on with the plotting. So we wanted to reload the data frame example, but wanted to make the parties be the index columns. So let's say, for instance, we have a data frame, let's call it Bundestag, with party as index. And for this, let's do pd.readcsv. And let's navigate to the Bundestag data example once again. So data/19 Bundestag. And then we have 19 Bundestag example.csv. And then we have a couple more options. So a lot more options how we want to read in that data set. And for instance, we can read in with the index column and then associate the index column to one particular column in the CSV file. And we might, for instance, be interested in using party here. And then by doing so, we will get a data frame, which is almost as before, but now it is using the party as the index column. And if we have it in that way and do the quick plotting, plot pi y equals seats, it will do it in a way that we kind of like. I mean, it failed a bit in putting the legend at the correct position, but at least it now named the chunks correctly. So this is what I wanted to show. So there are some more plotting options. You can also do line plots, but this is at least a convenience feature that Pandas offers. And now we want to move on to more plotting, but with a different data set. And I have another data set for you also in the data folder, which is called takeover trajectories, which are some artificial trajectories from a takeover maneuver from a car. And they are given not as a CSV file, but as a csv.gset file. And if you've never seen that before, that's a compression algorithm. It's called gzip. And it's a common way to store text-based files. Because imagine, for instance, you have large data sets. And this takeover trajectory is a rather large data set. And you want to save that as a text file. And in this text file, you tend to have many, many repetitive elements in there. And if you use a compression algorithm, you can put that down to a reasonable size and make these CSV files still manageable. And the good thing about Pandas is that it can also read in zipped CSV files, because it then will automatically extract it for us. So let's load the data set in. Let me check what kind of a naming we should give it. Let's call it trajectories. Sorry, trajectories, and say pd.readcsv. And then under the data subfolder, let's take the takeover trajectories.csv.gset. Okay, I failed. Takeover trajectories.csv.gset. I hope that is fine, should be fine. Okay, and then it reads it in, extract it for us, and then we have them available for usage. And let's take a look at them. So trajectories, and this is kind of prepared for you. I mean, just to give you a perspective, so that many things that we have here, although the Bundestag example might have had a mistake in there, but this data is, of course, prepared and in a format that we can easily use it. And commonly, if you want to do any machine learning, as we will also see tomorrow, this data preparation step is usually taking a lot of time and can be quite tedious. Okay, so what do we have here? Let me give you an explanation of the data set. So basically, we have put let's say, a recorder on a virtual car and have it perform some kind of maneuver at a certain time. It has a certain position in X and Y. So given we are, for instance, at time 0.03 seconds, it is at position X equals 0.44 meters and Y minus 2.5, almost 0. And then we not only have one maneuver, but we have 5 maneuvers. Again, zero-based indexing. So we have a trajectory ID as well. So we have a trajectory ID 0, 1, 2, 3, 4. And in total, we have 5,005 rows, which means each of the trajectories takes 1001 rows, which makes sense because it goes from 0 including 10. So it has a time stepping of 0.01, and then it has a 1001 steps, which makes it go over this 10-second length of trajectory. And in this 10 seconds, it kind of moves by about 213 meters. It's quite substantial. That's a good point. I think probably it's around 80 kilometers an hour or so. And we now want to visualize that. What we want to visualize is basically we want to have a plot where all of the trajectories are in an XY plane. So that's something you might be interested in. So you might want to qualitatively compare how the cars did these different takeover maneuvers. And I want to show you 3 ways. And but then we will see maybe what is the best way to do it, or the nicest way, or the nicest looking way. And the first one I want to do is using Matplotlib, because we've learned that before. And for this, let us first think a little bit about how we can do that. So we could, of course, do it manually, but this is kind of a task that might call for a for loop. And then you say, well, for loops, they are so slow. Why should we be using for loops? I mean, of course, at certain points, it might still be reasonable to use for loops. Here we have 5 trajectory IDs. Okay, so what we could do is we could have a for loop over 5 elements, and then extract the sub trajectory from the data frame, and then plot this sub trajectory using plt.plot, which gives us a line plot. Okay, let's do that. Let's try. For this, we have to do for, and let's say iterator variable I in range of 5. And then we have to extract the x. And now again, remember condition-based indexing. So I have to check where our trajectory ID corresponds to the given to the given iterator VN. On Slido, there is a hint that I was a little bit too fast. Okay, no worries, I can go back. So basically, what we had here, maybe I hope this is fast back enough. So we used Pandas to read in a CSV file which has additionally been gzipped, so basically compressed. That's why it's only having a significantly smaller footprint on your hard drive. And Pandas can unzip it and read it in for us. And then we took a look at it. And this data frame is, I prepared it for you in that particular way. This data frame consists of 5 different movements of cars on a 2-dimensional plane. So imagine, for instance, you have, okay, maybe let's draw that real quick, because that probably gives us a good understanding. Or maybe I can also a little bit hint what is going on. So here, this is probably what we're getting out here. So imagine it the following way. So you have a car. You have a street, and then you have a car here. So something like this. And then this car, maybe there is an obstacle, and then this car would perform something like this. So this in German, it's like driving on the right side of the road. So there the traffic is flowing in this direction, and here it is flowing in this direction. And so it's performing a takeover maneuver, and it is doing this at roughly 80 kilometers an hour. And then it is overtaking this obstacle that was here. And now we have that 5 times, but all the time a little bit in a different condition. So something has changed. I didn't tell you what has changed. I mean, this is not too relevant for the visualization purposes, but something has changed. And this then results in different takeover maneuver. And we want to visualize all these 5 at the same time. Okay, I hope that gave it a little bit more context. I will tick off the question. If it's still unclear, then please write a follow-up question. So And now we ask ourselves, how can we do that? So we now have the goal in mind, what we want to have. So we've also seen that on the slide. And the question is now, how can we do that? And the naive way, and often the naive way, it might not be a bad solution, is to iterate over and have an iterator variable that goes from 0, 1, 2, 3, 4. And then we have a conditional indexing to check whether the trajectory ID equals our iterator variable. And based on that, we extract the array of x coordinates and the array of y coordinates. And then we just perform a line plot or create a line plot based on that. Okay, so let's extract x by saying trajectories accessed when trajectories dot at trajectory ID, so many trajectory, is equal to I. And then, so this is basically, this is creating a slice, but it's including all the columns. And then we only want the X column. Okay, let's decipher that again. This one is creating a Boolean array. And this Boolean array has 5005 rows. And in the first 1001 rows, it is true. And in the last 4004 rows, it is false. And if we then use it to access our array, this will extract the first 1001 rows. And out of these 1001 rows, we only want the X column. So we use another indexing then. There's a question in Slido asking, is there a big difference in performance when reading compressed zip files and uncompressed data? It depends. It kind of depends, of course, on many factors, depending on what kind of a compression algorithm was used. It depends on whether you have some certain hardware components in your CPU that accelerate the decompression. I mean, in this particular case, if it's running too slow for you, then that might be an indicator that in this particular scenario, there is something wrong. But although it could also be something related to your operating system, in general, I think for this small sizes of files, there should not be a big performance hit when compressing or decompressing. So this should be rather quick. Of course, if you have larger files, then you of course have to kind of find a balance between the saved memory that you get by zipping, and of course also the added the performance decrease. And of course, always take in mind that certain file formats can't be compressed much. So, I mean, these text files, these CSV files, they usually have compression factors of 10 to 100 because there is so much repeating elements in them such that we can compress it easily. But for instance, if you have more complicated data like video or something, you usually don't compress that because, first of all, it already is somehow compressed. But if you want to compress it further, you usually don't get any benefit from that. But it's just some general advice that's not necessarily related to Pandas. Hope it is still helpful though. But thanks for the question. I think that's quite relevant since practically, of course, you have to make that decision for how you store the data. Okay, so we've done that with X. Let's do the same with Y. Similar strategy. Basically, first we extract the corresponding rows, and then we take the Y variable. And then we just have to plot it, plt.plot x, y. And I hope this also works now in the Jupyter notebooks the way I intended. And probably, since we get an error, we haven't imported Matplotlib yet. Or have we? I don't think so. So let's import matplotlib.pyplot as plt. And then with a shift enter, let's cross the fingers. Yes, it works. And then we get a plot, of course, without any axis labels, but it is just a proof of concept here. And so imagine again, this is kind of this bird's eye view on a road where we see the trajectories of the car. And for instance, the red car is taking an early takeover maneuver, and the other cars are taking a later takeover maneuver. And the reason I want to do that first is to highlight two things. First of all, we will now see different ways to do that. And you might prefer the way I show you now to do that. But if you think of something and you already know a tool or a way to accomplish the task, and it is not overly complicated, you shouldn't prematurely optimize. So I mean, of course, the tools I will show you now, they are, first of all, more handy, allow for more flexibility. But in the end, if you just want to get something done, it might just be helpful to go with the way that you think about it. And especially if you are really new to Python and to all these libraries and all this stuff, you might pick up some patterns on how to do things. Also, like from the way I show it to you. And sometimes they might not be the most efficient, the most effective, and the best way to do that. But still, it is kind of like good to stick with what you already know, and that kind of gets your stuff done. So it is not necessarily as kind of advisable to always sometimes stick to the boring stuff and not necessarily get, how you say, too strongly influenced by the fancy stuff. But I'm also like affected by those kind of things to attend to prematurely optimize. Either way, let's continue. Let's do the second one. I already highlighted that I want to use Seaborn. So Seaborn is, so let's import Seaborn as SNS. And Seaborn is just a library that was built on top of Matplotlib. So it uses the plotting functionality of Matplotlib, but it provides some more fancy interface. Well, not fancy interface, but it allows for more advanced stuff. So Shift-Enter to import that. Yes, that should work. And then we can use SNS, so Seaborn, to work based on the data set. So we do an SNS.line plot and then say the data is trajectories. On the x-axis, I want to have the column named x. On the y-axis, I want to have the column named y. And now the big idea is we have a U, and a U is kind of a way to group our data set into certain sub data sets. And well, sub data sets, but sub data frames, essentially what we did with the looping and the condition-based indexing. And here our U then of course is the trajectory ID. And if we let that run, we kind of get the same plot. I mean, it uses a little bit of a different color palette. That's of course adjustable. Maybe you prefer that, maybe you like that one more. But in the end, it plots the same thing. And it does that in one line. And that's also kind of the theme of Seaborn, that it usually builds upon Pandas data frames. So maybe also a little bit of an historical perspective. So in the beginning, there was probably mostly just Matplotlib and NumPy, and then Pandas and Seaborn is kind of like a more modern aspect of this ecosystem that you find in Pandas, in NumPy, in Python, of course. Okay, that you find in Python. There, of course, the focus has been on working with data frames. As far as I know, Matplotlib also now supports the way to just hand over Pandas data frames and then directly interact with the columns of these data frames. Although for this kind of stuff, I would still prefer to use Seaborn, since they also tend to have really nice default color palettes, which can also improve your visual quality of the plot. I mean, maybe not this one in particular, but so this is Seaborn. I now want to work with Plotly. If you remember, earlier I mentioned that Matplotlib, as of course Matplotlib and Seaborn, they have some, they kind of are similar to each other, but then there's Plotly, which uses something which has a completely different interface in comparison to Matplotlib. And by different, I mean like absolutely different. That also makes it hard to kind of learn Plotly, because the configuration, especially also when you want to do some more stuff, like for instance adding grids and adding modifying the ticks on a particular axis, this takes some more care to read into, and the concepts that Plotly uses are also really more advanced Python concepts. Still, I would like to show this to you. But first, I want to answer the question that was asked in Slido, saying, is it possible to save the figures from Seaborn as PDF? Well, I mean, I don't know it by heart, but we can just try to find a way. Let's see what we can do here. So here in that case, we can't save them that easily. So sometimes I don't remember this. I always forget that if it was in Julia or in Python. But in that case, we can access the functionality of Matplotlib. And that's also something you can take away from this. You kind of plot with Seaborn functionality, but in the backend, you still have Matplotlib. And I can show that to you, for instance, that we use Matplotlib commands after Seaborn commands. So for instance, here we can make plt.crit, and that should add a crit to the Seaborn plot. And based on that, we can, of course, then also save our plot by saying plt.savefig and say my Seaborn plot saved.pdf. And then we should be able to go to the Explorer and see, where is it, my Seaborn plot saved. And here we go. Here we have it as a PDF. And it even has like the fonts and the how you say, the fonts embedded in it. And I mean, as opposed as the good aspect of a PDF, you kind of have this vector graphics. I hope it's a vector graphic. I think so. Either way, so this so bottom line is you can use the Matplotlib functionality to access the plots created by Seaborn. Let's continue on with Plotly, and for this we will again work on the trajectories data set. But first we have to import Plotly. So we do import Plotly, and similar to Matplotlib, Plotly has multiple interfaces. Here we will use the Express interface, and then afterwards we will use the Graph Objects interface. So the Express interface, as the name might suggest, is the quick and dirty Express way of doing things. And the Graph Objects, we will see later, allows for more flexibility. So import plotly.express as px. And then we can do, sorry, I have to cheat a bit and see. Yeah. And then we have to do px.line. And line, here's a line plot. And you kind of see that all these three libraries have different namings, but that's what I mentioned earlier, that I mean, different developers tend to use different conventions. And here this line, for Seaborn, it was line plot. And then for Plotly, for Matplotlib, it was just plot. But I'm pretty sure this is something you will get used to over time. I mean, you will not get used to, but you will try to adapt to that. Okay, and this takes a data frame. I mean, here it's a little bit more verbose what it takes, and it takes the trajectories as a data frame. And then on X, we want to have X, and on Y, we want to have Y. Sorry, we want to have Y. And on the line group, okay, this is the U, and it's now called a line group. Weird. And then we have the trajectory ID. I hope that works. Let's see. And here we go. And here we have Plotly. And you probably see that the interface is way different from what it was with Matplotlib. And here it's super nice. I haven't used Plotly that often in Jupyter yet, but it really embeds in how you would see it in a web browser. I will show this to you in a second. And first of all, you have this really interactive charts where you can hover over and see certain values at certain points. We have many different options. You also have an options to directly download it here as a PNG file. That's quite cool. Yeah, but basically it returns the same. Of course, here it didn't use a color scheme. That's just because it didn't do that by default. Of course, you can do that, but won't be doing it here. And I mentioned that Plotly has really a lot of options, a lot of things that you can do. But the good thing about Plotly in comparison to the other two libraries, I mean, Seaborn is not that bad though, but Matplotlib in particular, is that the interface is vast, but it's not as well documented. I mean, it is documented, but it might not be documented in the way you would expect a modern Python library to be documented. And if you recall from the section on functions yesterday, I told you that these keyword arguments are often used with sensible default values, in particular, for instance, also with Scikit-learn. And this is what you can see here. This is kind of crazy, isn't it? So this is the line function, and this is all the options it has. And it's not even all you can do with Plotly, but it's just the option that this function has. And you say, for instance, well, data frame by default none, and yeah, I think all of them are by default none. I mean, at least some others. Of course, a lot of them I don't know by heart. I don't know what they do. I just trust that the default values are sensible. And in case I want to modify something, I tend to have to look up in the documentation. But at least the good thing here is, and why I like that so much, if you have these keywords by default values, your auto-completion engine, for instance, in VS Code, can suggest what you want to do. I give you an example. So let's say, for instance, what should we want to do? Maybe, let me see, what should we do? Maybe, I haven't tried that yet. Let's just see if that works. Let's try color and put color. And okay, so the point is, if I am at COL and hit control space, it kind of gives me the, it kind of gives me the auto-completion suggestion. And then we can make the color, maybe that works. I haven't tried that. Let's see. Oh yeah, oh cool. Yeah, see, sometimes you have to trust. And here now we also have a different color based on the trajectory ID. Yeah, so bottom line is, it's good to have a lot of options, but then it can be like, it's kind of like helpful to have them as these default values. And I hope this that you also have like all these auto completion tools. Sometimes they might be a little bit buggy, but I think if the installation with VS Code worked smoothly, then you can just hover over and then get the preview. I like that a lot. It's such an helpful tool. Oh yeah, for instance, we could maybe, if you're also trying this out, maybe we can make X a log. So log X, maybe true. Let's see. Is that working? Oh yeah. Yeah, okay. Yeah, of course, it does not make sense, but at least you have so much option to play around. Yeah. Okay, great. So then I would finish in the Jupyter notebook, and we can now move to the IPython shell once again. Yay, to do the 3D plots with Plotly. And so let me bring up the Python shell, then go to the terminal, and then let's go into my Python session. And inside this interactive Python session, I want to show you how the Plotly interface is usually without outside of a Jupyter notebook. And in this, I want to have a super simple 3D plot. For this, let's first import NumPy, because as always, we need NumPy for the computations. And again, this should show you the theme. NumPy is the basis of almost all scientific computing in Python. And then we need the Plotly graph objects interface. So import plotly.graph objects as go, graph objects. And this is another, I said this is another interface. This allows us to do the 3D plot I want to show you here. How should we do a 3D plot? Well, let me first show you this in the slides, what we're going to do. If you've never done this before, this might be a bit confusing. Where are my slides here? Okay. I don't want to spoil how it is done, so let me do that right next to the trajectories. And so basically what I want to do with you is that we have a three-dimensional plot, so with an X, a Y, and a Z. And I want to show you like the super classical example of a paraboloid. My drawing is terrible, but maybe if you remember that from some multivariate calculus, this is like the parabola in 2 dimensions. And this is basically, in order to get that, we say that Z is equal to X squared plus Y squared. We can plot that on a computer. So, I mean, we plotted earlier the line plots by creating a table of values. And here we have to create a mesh of values. So we kind of have to mesh our 2-dimensional plane. So this is our plane here. So I'm trying to, this is in the XY plane. And here we then have to create a mesh, something like this. So a mesh, maybe like a super simple I think you get that, like a Cartesian mesh. And at each point in the vertex, so what is a good color? Maybe this one. At each point in the vertex, we associate the point on the parabola. And then if we have 4 points, then, yeah, terrible. Maybe let me show that to you in this way. So if we have one of these squares extracted from here, and then we have the corresponding values attached to that, we can draw an quadrilateral, that's usually how it's called, in 3D. Kind of, it's like it's a shifted, rotated, whatever rectangle. And this is a primitive in computer graphics, and that's what Plotly is drawing for us. So what we have to supply Plotly with is the mesh and the corresponding values of the set point. And that's what we will be doing here. So a quick recap again. So we are going from 1D to 2D. So we no longer need an interval, but we need a 2D mesh. And at each point, at each vertex location, we will attach a z coordinate. And then we can plot in 3D. Sounds cool? Let's do it. Okay, I will go over to Visual Studio Code again. And for this, we first have to discretize in X and Y direction independently. Then we create our mesh, and then we associate the set coordinates. So let's do X and say, for instance, we want to have X numpy linspace -3 to 3, 100. Yeah, 100 points. Y going to be numpy linspace -3 to 3, 100. So if you forgot, linspace was for linearly spaced. So from -3 to 3, give me 100 points, where the spacing in between the points is identical. And then we can use a function from NumPy in order to mesh these two intervals, or not intervals, but arrays. And then we get an x, y is given as np.meshgrid x, y, and I've gave them capital letters. Capital X, capital Y is np.meshgrid of lowercase x and lowercase y. Hit enter. And then if we look at the shape of x, this is 100 entries or 100 dimensions in the first 0 axis. And if we look at the shape of capital X, it has 2 axes and 100 dimensions each. And in that particular case, this refers to the X coordinates of each point in our 2-dimensional mesh. And Y refers to the Y coordinates. And then we can query the set points as x squared, so capital X squared plus capital Y squared. And recall, this is nothing else than what we did before, vectorization and broadcasting. So we have the vectorized power operator, which takes the power in element-wise. And this is crucial for the MATLAB users here, that power in NumPy is element-wise and it's not matrix power. And then we have the add, which adds up the elements element-wise. So element per element, element per element. And then we have set, which, sorry, maybe set.shape would be more reasonable to use here. And then this is also 100 by 100. Now the computations are done and we can finally start visualizing. And for this, I want to create a figure with Plotly. For this, I will do go.figure. And then this go.figure takes a figure object. And here I want to create a surface plot. So go.surface and say x is lowercase x, y is lowercase y, and z is capital Z. And this will then create a variable. And I hope this also give you some perspective. Like earlier we had the question, how do we save a plot in a variable? I mean, you can, as I said, you can do that with Matplotlib, but the interface is, it's not really 100% clear, at least to me. Here in Plotly, it's way more obvious. It's kind of the way it has to be done. So we have to save that in a fig variable. And this figure variable contains all the information. So you see it's kind of a dictionary, and there's the data inside, and then there's also the customization of the layout, etc. And then in order to show that figure, so maybe first if we haven't copied that, so fig equals go.figure, go.surface, x equals x, y equals y, z equals capital Z. And then we can do fig.show. And if you hit enter, this will bring up a web server. Sorry, a website. And here we go. So this is the website. Let me see. Okay, so it's not in the best aspect ratio. We should have done some modifications to the layout, but I think you get the point. So now we have a 3D plot, and it's so nice. I like these 3D plots a lot. Like the color, the shading, it's beautiful. And you can move that around. And here we kind of see our parabola and or paraboloid. And in that case, it is, of course, a little bit different to what I've drawn in the slides, because we are using a rectangular base domain or like a rectangular mesh, whereas in the plotting, I kind of use something that is rotationally symmetric. But it's cool. And we again have the similar Plotly features that with the highlighting, and we even see contour lines. It's beautiful. And of course, you can then also like save these figures. I think it's called fig. I think it's called write image. Let me see. I always forget if it's save image or write image. But let's take an example from plotly.png. And there you see it requires an additional library called Kaleido in order to export that. Feel free to install it and try it out, but it works also that way. One particular emphasis I want to bring up here is, I mentioned it a couple of times, it's hard to custom. I mean, it's not hard, but it can be a little bit troublesome to customize it. And for this, I want to look at the example review, how to change to an cube aspect ratio. Because if we look at the fig.show, you kind of see that the aspect ratio is kind of screwed. So we kind of have this. So in essence, the Z axis is taller than the other axis. And I want to have the aspect mode as a cube. And now assume, I mean, to be fair, the preparation went well, so I'm not even prepared for that. So I don't know that, but the point is I wanted to show you how I would retrieve that information. And for instance, what we could do, we could either directly ask for our problem, I mean, ask, like Google the question, or we could just go for the documentation online. So I like to go maybe Plotly, layout, it's called a scene. I mean, I already know that. It's kind of an advantage on my side. Scene reference. And then layout.scene. Maybe this helps us. Let's check. Here we go. And there we have the Plotly reference. And you see it's large. So I just try to give you a perspective of what you can do with Plotly. And this can be overwhelming. Absolutely. Maybe if we Google or search, I did Control F if you didn't know, like you can search within web pages, and then I do aspect mode. Oh, that's good. Aspect mode. So it is aspect mode, but it is aspect mode not on the highest level. We actually have to check what is the highest level. So the highest level is scene, which means we have to nest scene and aspect mode. And then we have to set the value of cube. So here it says aspect mode, type enumerated, one of auto, cube, data, and manual. And the default is auto. And it turned out that auto did not give us a visually pleasing result. And then it says if cube, the scene's axes are drawn as a cube, regardless of the axis range. That's what we want. Okay, let's go. Take this here. Oh, maybe let's show. Okay, unfortunately, I can't keep it in the foreground, so I move it on the other monitor. And we can do figure.update layout. And again, this is kind of the advantage here, which I also prefer on Plotly, that we have everything stored in this variable. In the interface I've shown to you with Matplotlib, this is not that easily the case. So because then you have this stateful. There you have the stateful machine, and you have to do this PLT. Okay, so we want to update the layout, and we want to update the scene, and then the scene aspect mode, and we want to set that to cube. And here you see we had these two hierarchy levels. We had first scene and then aspect mode, and I'm using an underscore to differentiate or to separate them. And then I hit enter, and a C. Now it has changed the layout and cube. In case this printout is too much for you, just add a semicolon at the end and the printout is suppressed. And then we can do figure.show. And here we go. Hopefully it works. Let's see. Oh yeah, that's gorgeous. I like it. And as you see here, so now we have this cube aspect mode. And I mean, of course, this, at least for me, this was the first what I was thinking about. We want to change something in that regard. But the bottom line is, it can be harder to navigate the options, but you can do way more with Plotly. And I also personally like that it's more obvious. Of course, there's a steeper learning curve to it, but it feels to me that Plotly has a better design on the interface. Or maybe I've just incorrectly learned Matplotlib. There's also a certain chance there, and I've put more time into learning Plotly. But yeah, I like it. It's beautiful, especially also with if you want to do fancy plots. Not fancy, but like more advanced plotting than just scatter plot and line plot and so on. Because as said, just to give you like my point of view on that, you might have a different one and it's absolutely fine. As said, I use Matplotlib mostly for quick and dirty plots. So like just some scatter plots, some simple line plots, maybe a bar chart. But most of the time when I need something more advanced, I will resort to Plotly. Okay, there's the question on Slido. Can I export Plotly graphs as scalable vector graphics? So this is an SVG. Good question. I don't know. Let's try. Let's see if what Plotly says. Plotly export as SVG. So static image export. That's what I meant. So there it also says you need this Kaleido. Probably we can quickly install it. Let's say pip install Kaleido. Yeah, it's a rather large, and it's rather large because it's interesting, by the way. Plotly uses the web browser to render things, whereas Matplotlib uses GUI packages, and GUI packages are like, for instance, Qt or GTK. And if you followed us in the first break, we tried to change the backend of Matplotlib, like the way it renders stuff. And Plotly is so nice because it uses the web browser, and almost everyone has a web browser installed. It's just a neat way of doing it. But that kind of makes it hard to export images because you could export them directly from the browser. So for instance, you could go here and, well, type the download as PNG, but first of all, you can only download as PNG. Oh, maybe let me open that. Okay, it opens it in GIMP, but at least, you know, you get the PNG file. But you don't get the SVG. And of course, you always need to first go to the web browser. And this Kaleido is basically just a super small web browser, which renders the image for you, easily put. Anyways, let's try to export that and see if it exports us as an SVG. Maybe let's see SVG, vector formats, and there it says write image and then just SVG. And let's just do fig write image and say my vector graphics.svg. And oh yeah, I see. Probably it has to, you have to reload the, maybe if I import Kaleido, I don't know, maybe then it can understand that. No, you have to restart the IPython shell. I'm sorry for that. Maybe we can quickly do that. So I will hit Control, or maybe open another one here and do IPython conda activate Python course, and then do IPython import. Let's just make some super Plotly express plots here. Sorry, spx, and then say fig px dot line, and then do x 1 2 3, y is 2 3 1 maybe, and then take a look at that. You will get this plot, and let's just export it fig dot write image and say my vector dot svg. And bam, it worked. Let's go to the file explorer, and then we see my vector.svg. And of course, I can't preview that in Or can I? No, I can't. So maybe let's open that up in GIMP. GIMP my vector SVG. And let's render it, and then you have an SVG file. I mean, here it is pixelated because it is rendered out, but you can use it as SVG file. So kind of you can, I mean, bottom line, of course, is probably if there is a common use case for something, it is implemented in a Python library. So also exporting stuff in, I mean, not exotic formats, but in the common web formats like PNG, JPEG, PDF, SVG, you name it. Okay, is there another question? Let me check. Then I would tick that as answered. And thank you for the question. That's a good question. I think it's really, because SVG files are a good way to embed them in papers, because it's first of all it's a vector graphics, and then it's also including all the text. Although I think you can equally use PDFs for that. Last but not least, before the lunch break, I want to introduce Streamlit to you. I already teased that, as I like the way Streamlit does a lot of things. And for this, we will also be writing a script and a script, so a text file. So now we finally go back to scripts. I hope this kind of makes those people happy who voted for their preferred way as scripts earlier yesterday. I want to do the following application. So in case you remember, maybe I can also show it to you real quick again. If we look at the Pandas example, we did this plotting with the different trajectories. And I want to create a web app where you can have a drop-down menu or a slider, and you can select the trajectory ID. And based on the trajectory ID, it will plot the trajectory. I mean, of course, you could have also plotted them all at once, but this is just a proof of concept. And in order to get that, we will first have to write a small script. So for this, let us create a new file here, and let's call this a super fancy Streamlit example. And then, of course, .py, because it will be a Python script. And then I will close the file explorer. And then probably, since initially when I create the preparational videos for the course, I did not include Streamlit initially, but I thought it would be a nice extension. So you probably don't have Streamlit installed. So first run pip install Streamlit. Of course, you have to be in your environment for that. And then it should install that. I mean, for me, it's already installed. It can take a bit. And just as a disclaimer, the very first time we're going to start Streamlit, it will say, hey, what's your email address? But you can just hit enter and you don't have to enter anything. So just that you are prepared. Anyways, let's go to the plot, to the script. And for this, what we need, so what kind of functionality do we need? Let's make an overview. First, we need Streamlit itself, because you want to write a Streamlit app. Then we need Pandas in order to read our CSV file. And then we need to visualize it somehow. And I'm a little bit opinionated towards Plotly, so I want to use Plotly. Okay, let's do import Streamlit as st, then import pandas as pd, and then import plotly.express as px. And then the cool thing about Streamlit is that many things that are difficult when you write GUI applications are actually quite easy with Streamlit. And let's first start by setting the title of our web page. So let's say st.title, and maybe let's say hello and welcome. Not hello world this time, hello and welcome. And then let's say, for instance, st.write, it just writes out the text passage and say, this is my first Streamlit app. That's a lie. It's because it's not my first Streamlit app, but maybe it's for you. And then we read in the trajectories. So trajectories is pd.read CSV, and then data. And then in the data, I want to read in the takeover trajectories.csv.gz. Because it was this zipped file, I want to start with a slider so that the user can slide which trajectory it wants. So let's do the chosen trajectory. And that's the cool thing about Streamlit. I believe it's quite intuitive. So we want to save the result of the slider in chosen trajectory. So we instantiate the slider as chosen trajectory. So we do st.slider. And then I want to go to the new line just to be, just because we have a couple of options to this. So first we have to provide a label, which is which trajectory. And then in the next line, I want to say the minimum value. So what is the lowest one you can have, which is 0. And then the max value is what, 4. And I shouldn't be using space in between. This is actually, according to the PEP, if I remember PEP 8, you should not be using space in between these equal sign and the variable name. Then the step should be 1. So this is basically, you go from 0 to 4, and we can go in 1 step. So 0, 1, 2, 3, and 4. And then value, which will be initial value, which shall be 0. This chosen trajectory will now be an integer. So depending on which kind of value the user has chosen with the slider. And then we can create a figure by using px.line. And then we provide the data frame. Then we provide the data frame, which is trajectories. And then the x coordinate shall be associated with the x column, the y with the y column. And then we have the line group. I hope that works. I've done a little differently. If that doesn't work, then we have to resort to the way I have it in my script. And the line group is then the chosen trajectory. Yes, no, that's probably not working. No, I think we have to do it differently. So we have to kind of do it in the way we did it with the for loop, that we first extracted the x coordinates and then the y coordinates. So first, let's take the trajectories and access it at where the trajectory ID, so this condition-based indexing, is going to be the chosen trajectory, and then access the x coordinate. And then I will just copy paste that line and change that for the y. And then we can delete this line. So same idea as we had, the same idea compared to what we had in the IPython notebook. So we did a condition-based indexing to extract all the rows that are associated with one trajectory ID. And then from these rows, we extract the column that is associated with x. So the x position in our two-dimensional, on our two-dimensional road. Okay, then use Plotly in order to create our figure. So let's say figure is px.align with x being x and y being y. And then we use st.write in order to add the figure to our Streamlit example. And then I will save the file, and I will give you 1 or 2 more minutes to catch up, because I'm pretty sure that for some it might have been a little bit too fast writing that down. In the meantime, I will just quickly recap on what I wrote down. So first we have the imports, because so far I think we've never properly done a Python script. So we have first the imports, and then we used st for various kind of functionality. And here we first wrote out a title, then we used write in order to write something to our app. Then we created a slider, which is one of the GUI elements that st provides, Streamlit provides. And then I created a figure that I added to our Streamlit website. And of course, the rest of it is quite similar to what we've done with the IPython notebooks. And that's a minimal worker example here for Streamlit. I mean, of course, the first 2 lines wouldn't have been necessary, but this is just to give you some context on what can be done. Okay, and then let's execute the Streamlit file, but we shouldn't be executing it with Python. We need to execute it with the Streamlit way. So this means we use Streamlit and then say Streamlit run. I think it's called run. We will see about that in a second. Super fancy Streamlit example. And you hit enter. If that does not work for you, then try Python -m Streamlit run, super fancy Streamlit example. And just give you a couple of seconds. And once you then hit enter, and if you have never used Streamlit before, then it will ask you for the email address. And don't enter anything, just hit enter. And then it will bring up a web server. It will start a web server and it will bring up your web browser. So I will hit enter. I hope it works. Yes. Oh yeah. Okay. It already tells me I should upgrade, but it's still working. And isn't that nice? Since a couple of updates, Streamlit has dark mode, and I like dark mode. Okay, here we go. That's our app, and it's kind of responsive, kind of. And I will just enlarge the browser. And basically, this is a super simple app. So we have our hello and welcome, then we have this written down, and then we have the slider, and we have the plot. And the plot even has the functionality of Plotly. And then we can move the slider around and change the trajectory. I think you get the gist. So this is allowing us to modify that. And you can make so many nice applications with Streamlit. This is a crazy tool. I mean, was kind of a game changer for me, especially how I do GUI applications. I mean, maybe some dislike it, but it's hard for me to believe how you can dislike such a nice app. Okay, feel free to play around with that. You also have all the options that Plotly has. You can maybe zoom in here or reset the view, or pan around if you want to. If that was a little bit too fast, don't worry. After the lunch break, I want to go over it once again. Let's just head over to the slides for a second to quickly wrap up before we go into the lunch break. For this, we did the 3D plots, that's fine. I just want to quickly, maybe let's do the poll. I think that's going to be a nice question right before the break. And please participate. So let's have a poll in what kind of library you preferred. So we have 3 options. So don't tick 4. Don't disappoint me with that. Let me see, where is my results window? So the question is, so in case you just continued writing, so which of the presented plotting libraries did you like the most? I mean, you haven't seen much of them, so it's kind of like a preliminary perspective on that. So we have Matplotlib, which is kind of the classic way of doing it, which also, on top of that, which also has an interface that is quite similar to Matlab, which might be helpful for many people trying to transition from Python to from MATLAB to Python. Maybe also the other way around then. So then we have Seaborn. As said, this is kind of built upon Matplotlib, has some nice additional functionality. And we have Plotly. I called it a new kit. I don't think it's that new anymore. And the majority of you, interesting. I mean, we only have 16 participants, but now it's getting a tie here. So we kind of, we have a tie on now Matplotlib took over. Now it's tie again. So, at least we see that. I hope I could at least show you the classical way it's done. There are also other plotting libraries. I will highlight that in a second, but I think that Matplotlib and Plotly probably make up 80% of what people do in Python. I mean, I don't have any statistics on that. This is my personal perception. Okay, very cool. Thank you so much for the participation. Then let's just go over, as with everything, what we haven't done yet. So in Pandas, I mean, it's Pandas. I told you multiple times that I myself, I only think I scratched the surface of Pandas. So some interesting things you might want to spend some time on are data frame joins. I'm honest with you, up to this point, I haven't fully understood them yet. But this also means I've did a lot of data mangling so far, but I got around that without it. Probably it would have been easier with using joins, but so just you can look into that. And then a lot of data cleaning aspects. So for instance, batch type conversions, and like for instance, usually when you have data, you might have rows where information is missing. And Pandas has many functionality in order for you to detect that and to work around with that. Then we have grouping, which allows you to create grouped parts of your data frame. We did that kind of indirectly when we looked at the use with Streamlit and also with the line groups in Plotly. So under the hood, what they do is they use the grouping functionality of Pandas, although we did not do it explicitly ourselves. But you might be interested in that. So then Seaborn, I think one of the big advantages of Seaborn, which I didn't show you, but is or definitely also a selling point for it, is the statistical plotting. So when you have, statistical plotting, what does that refer to? So for instance, many options for plotting standard deviations. For instance, what I like a lot about them, how easily they do it if you have trajectories like this, and you have a continuous error bar. So something like, there's like this. I mean, probably you have seen that some point where where this is shaded, something like this, a continuous error bar, instead of having element-wise error bars, something like this. Probably you've seen this once. Then with Plotly, I mean, we looked at Plotly Express, so this can go out. There is something called, it's the third major interface to Plotly. It's called the Figure Factory. There are some templates for many advanced use cases. And these templates, for instance, include streamlines. So if you want to plot your vector fields from CFD simulations or whatever you have, you could use Plotly for this. And since Plotly overall has a better performance than Matplotlib, it might also be reasonable to use at least for medium-sized problems. And then there is Dash. So Plotly has something similar to Streamlit with Dash, but the last time I used it, which is now 2 years ago, you had to pay for it. Maybe they have a free tier now, a community tier, but it's only hosted on the Plotly servers. And yesterday we had people that with concerns like hosting applications or doing stuff with on US servers, or I think they are Canadian, but Canadian servers. I can understand that, but rest assured, the Plotly Python library is independent of that. So the Plotly Python library, at least to my understanding, to my knowledge, has nothing to do with any US or Canadian servers. It was like this earlier, but they detached that at a certain point in time. And then some data science aspect we did not cover, like with SQL. And I'm pretty sure that if you want to dive deeper into this, then you can learn that. So SQL is a database accessing language, and there are tools within Python in order to perform that efficiently. I myself, I just have never used it. It's because I also found my data science aspects have always involved CSV files or something kind of CSV files. And therefore I've gotten around SQL. So there's also not much I could tell you about it though. But the only thing I can tell you is that it is important, especially if you want to do that in a business perspective, where many databases can be accessed with SQL, sometimes also pronounced SQL. Okay, then we looked at Streamlit. So this is just a Streamlit here. And it's super versatile. Just give me like 1 or 2 more minutes. I just want to show you what you can do with it. Okay, here we go. Now I can click the links. So I did a lot of examples for my YouTube channel because Streamlit can also, oh yeah, this does not work. Never mind, I will show it to you after the break. So you will also find great examples of others created online. And I'm kind of a big fan of those from an educational perspective, because I believe that this visual way of teaching stuff, especially if it is interactive and accessible for everyone, can be extremely helpful. Then we are back on the slides. Let me get my pen. Recap real quick what we've done so far. So we started today with Matplotlib with some basic plotting. I just gave you a little bit of a recap. For some, it must have been novel. For others, might have been not too advanced. And then we had that issue with you don't see my plot. I saw the plots, unfortunately, but you weren't able to. Then we moved to Python notebooks. And then after some time, we entered Pandas, Seaborn, and Plotly. So Pandas for the data-intensive task, and then Seaborn and Plotly for visualizing our data frames easily that we get from Pandas. And then we also looked at some other Plotly concepts. So for instance, how to create 3D plots. And then based on the poll, I think if I remember well, it wasn't like by a large amount, but at least it was the majority that I could convince to at least keep Plotly in mind. I can understand that maybe if you are new to Python, Plotly might feel a little bit overwhelming, especially also when we looked at the documentation, which was vast. So there's a lot of things to do. Okay, now after a little bit of recap on Streamlit, I want to go into SciPy. And I think this will take us about an hour approximately. And so we should be able to, hopefully, let's see if there's not anything in between. We should be able to start a little bit with Scikit-learn today already, and then continue with that tomorrow. Okay, so right before the break, we wrote that little Streamlit example here. And I hope that one worked for everyone. In case it didn't, I just want to go over it really quick again. So we first had our imports with Streamlit, Pandas, and Plotly Express. Then we used the functionality of Streamlit in order to do a little bit of a layout of our file. And then we load in the trajectories data frame. We created a slider, and then we extracted the X and Y coordinates of the trajectory based on the trajectory that was chosen with the slider. And then we created a figure using Plotly and displayed that figure in our web page. And here with Streamlit, so this is kind of running a server in the background. So let's just stop that with Control-C. And I just want to add one thing to this script, which is commonly done if you have like just script that run plainly in Python, as that is the case here, that you create a name switch. So what we do here is we have to kind of circumvent that the steps that we have written down here are also executed when we would hypothetically use this Python script as an import. Okay, this might seem a little bit confusing, but just let's add that here for completion. So for instance, you could write if __ name equals, and then in quotation marks, __ main. And then since this is a conditional statement, you have to indent all the lines that follow. And what this basically does is whenever the Python interpreter sees that file, it tries to, well, whenever it sees that file, it sees also that check here. And only if the this file is really executed with Python and then super fancy Streamlit example, then it will also execute the subsequent block. And it would not execute that if it was to import that module. So for instance, that means if you are in an IPython session and were to do from super fancy, for instance, to import super fancy Streamlit example, then it wouldn't do that anymore. It would do that though if we didn't have this switch here. So it's just like a common thing to do. And we will also see that in the next scripts that we then write for the Scikit-learn section. So I will save that real quick. And I hope, as said, with Streamlit, that kind of give you a little bit of motivation to look into this in more detail, as I think it's a nice tool in order to present research findings, for instance, some data, or also some methods if you have. It's commonly used, for instance, with machine learning. And I wanted to show you something. I will quickly try to maybe open that here. So for instance, here you could have an overview with some sliders that actively change plots, and it also kind of helps in if you want to convey some ideas. I like it a lot. Maybe you find a nice use case. There are many use cases for this, since you can not only just have plots, you could also include, for instance, tables, display data frames kind of natively, have maps also if you have some geographical data, and all of that in that regard. Okay, then let's close this Streamlit section. In case you want to take a look at that plot, you're curious, I've also pasted a link in the video description, in the chat, in the sub chat. And then we can go on with the SciPy section. And before we start with the Streamlit, with the SciPy, I wanted to give a little bit of an overview of the history in Python. I briefly mentioned that a couple of times, but just to have that kind of once again. So the idea, or Python, is kind of comparison to other programming language, and also including Matlab. It is a rather young language since it was released in 1991. So it's a little over 30 years now. And initially, Python was not designed for array computing. I mean, indirectly, that is kind of clear because we have this rather slow performance, which is relatively necessary if you want to do any technical computing, not necessarily scientific computing. And then there was a first array computing package called Numeric, which tried to introduce a lot of features that you might need to make Python kind of the scientific language as it is right now, like binding the arrays from lower dimensional, from lower languages like C or Fortran, and also providing access to high efficiency numerical algorithms. And then there was another package called NumArray, which provided many of the same functionalities, differed in a few aspects. And then in 2005, so about 15 years ago, those packages were unified into NumPy. And actually, the creators behind NumPy and also SciPy, they share many developers between them. Those are also the guys who created Conda, so Anaconda or Conda, which is this package manager you probably used for installing Python if you followed the preparational videos. And those guys that created the Conda, they're also now responsible for an organization called NumFocus. And I just wanted to show this to you real quick. And for instance, if you go on their website, NumFocus, that is basically an organization. Sorry, NumFocus. That is basically an organization that has the goal to to support or to organize open source software development. And they support a lot of projects. Maybe we have an overview, explore the projects. And many of the projects you find in here are really high quality numerical or scientific libraries. And those are supported like financially and also administratively throughout this organization. And the reason I'm showing this here is that kind of like with NumPy and with SciPy, it was also kind of the spark of having this well-organized, open source and freely accessible development of scientific libraries. And many of the libraries that you find in here are like best in class in that regard, especially for free software. And they cover many of the functionality you might have been doing with MATLAB toolboxes, at least that I am aware of. And in some parts, they also exceed the functionality of those. So in case you're curious, I would advise you to maybe take a look around. Maybe you also heard about them before, but just cool to see kind of how this all fits together. Let's go back to the slides. And I already said that NumPy is this access to lower level code in Fortran, C, and C++, kind of made easily accessible. And on top of that, there are like many numerical algorithms that could potentially be interfaced in these lower languages. And at a certain point, it was just unreasonable to keep them all in a NumPy installation. And so the developers decided to create this SciPy, which is really the collection of so many numerical algorithms. I just took a screenshot of their website. This is like from mid last year. Maybe it's changed a little bit. And we have different kind of sub packages. And I just want to highlight a couple. So we have a package for fast Fourier transformation. As far as I'm aware, they're using the FFTW package, which is probably one of the fastest fast Fourier transformations out there. You have packages for integration. So these are integration in the sense of integration of integrals, so quadrature, but it's also integration in sense of ODE integration. So there we have ODE solvers, and in MATLAB, for instance, you might have this ODE, I think it's called ODE 4.5, and of course, this is also accessible in there. They have probably most of the functionality that you would also find in MATLAB, and it's of course because in the end, both are using the same implementation. I mean, by implementation, I mean they use the same Fortran library to call for the ODEs. Oh, sorry, I could be wrong about that, but at least some of the functionalities share the same Fortran library between MATLAB and SciPy. Then we have some interpolation tools. That's clear. Then we have another linealc module. And this could raise the question, why do we need another linear alg module if we already have linear algebra within NumPy? So there's like more linear algebra. So if you remember, like this linear algebra in NumPy was rather small. I mean, you had the essential stuff with some essential matrix decompositions, but here you have a vaster option. We will look at optimize in a second. So this is a package for optimization and root finding. Then we also have signal processing tools. I think interesting also is to look at, I can also use the highlighter here, to use at the sparse package, to look at the sparse package, which contains sparse matrices, sparse arrays. So for instance, for solving partial differential equations and doing sparse linear algebra. And then later we will also see the stats package, the stats package for statistical functions, statistical programming, just to give you an overview. I selected those two because it's kind of has a closer relation to the machine learning topics that we are looking at later. However, as said, it's so diverse, it's almost impossible to cover everything here, but the documentation is mostly great, and we will try to have a look at the documentation also as part of this section. Okay, based on that, maybe I can convince you. Let's have a quick poll. Especially for those, I think approximately 50% of you would tick that MATLAB is their favorite programming language. Do you believe, or could it at least convince you to a certain degree that our MATLAB clone is complete by now? So we'll bring over the results, and we have the majority, 50% of you answering it depends. Well, certainly it depends, but maybe I thought maybe it's like, what is your opinion as of right now? But of course, it depends on what particular things you want to do. I'm pretty sure, at least to my experience, there is no really good free alternative to Simulink. So if this is something that you rely on, it's probably hard to find an open source and Python alternative for this. Although, of course, you could argue that many of the things Simulink do, you could also do just by programming it. But I think the big advantage probably of Simulink is that you have this graphical interface and program graphically, and you don't want to give that up. I don't know, maybe, I don't know if this is what was the major point for you in that poll. Thank you for participating. At least we got a little bit towards Python with this, it depends at least. Then let's start with simple optimization. And we want to use some super simple optimization algorithms. So for this, let's maybe first start with some theory in there. And we want to look at optimization problems. What does that mean? So I will just add that here because the next slide already shows the solution. And we will first start with one-dimensional optimization. So we have an x and we have an f of x. And there is a function. So for instance, this parabola, and we try to seek a minimum of this function. And analytically, of course, we could, so this one is given as f of x is x squared. And analytically, of course, we could take the first derivative, set it equal to 0, and solve for x. And in this particularly easy case, that is possible. However, here we want to use a numerical algorithm, which tries to find the optimum of this function, and optimum in this particular case refers to the minimum. So let's just do that. So let's head over to Visual Studio Code and let's expand or maximize this panel size. I will just quickly clear my screen, enter in a Python session. You can also use your previous one if you like. And here, let's import SciPy optimize. So you can kind of think of as SciPy as this large collection of submodules. So we want to import from SciPy import optimize. And then optimize is this collection of optimization algorithms. And in order to perform an optimization, we need to define our target function that we want to optimize. And in this case, let's call it, for instance, f. And let's use a lambda for this to also refresh that. So x shall be given as x squared in that case. And then let's do optimize and say minimize scalar and apply that to the function f. And then we get a result, basically. So what it returned was kind of a results object. And in there we see that it found the minimum at position X is 0. So this is, I mean, it's a super simple example, but it kind of worked. It says success equals true. I mean, an optimization can fail, so it could also be wrong, could also be false. And we see how many times it called the functions and also how many optimization iterations it took. That depends, of course, on the particular algorithm it has chosen. And this optimization result, we can maybe also store it in a variable. So let's maybe call this optimization result and say equals optimize dot minimize scalar on F. And then you see this optimization result. You can also look at the type of it. Is this, or it's called optimized result. And it's quite helpful to investigate that if you perform optimizations, since clearly oftentimes you struggle with finding and with converging to a solution. So you might have to adapt certain things. So let's go back to the slides. So because the reason I said I want to focus on optimization a little bit, because I also want to try to relate the subsequent machine learning examples we're doing to the optimizations that are necessary for this. So here I said we looked at the simple optimization, and I just wanted to give, I mean, a super simple overview on why optimization can be tricky and also how this is reflected in the implementation of SciPy. So generally speaking, when you want to do optimization, there are a couple of things that could vary. Depending on the algorithm, you choose, you can either have a gradient-free optimization, first-order methods, or second-order methods. You have to kind of think of it as if you have derivative information available. So you could, for instance, also, like loosely speaking, if you have again this, if you again have the parabola here, you could, for instance, just find the minimum by evaluating at many different points and then just cleverly trying to navigate to those which have the lowest value. In essence, this is what a lot of the gradient-free algorithms perform. You could have first-order methods. First-order methods are those that try to have that use the derivative information. So, for instance, you would start an optimization. Since optimization is always kind of an iterative procedure, you would start it at this position, for instance, and then your if you use kind of the tangent as your gradient information, then your tangent is applied in this direction. So the gradient is pointing upwards and we have a positive slope. And if you were to follow the negative, negative slope, so kind of in that direction, this would move you towards the minimum. I mean, this is of course quite trivial in this example here. And this is called a first order method. And the typical example, as we will then see in the deep learning section, is going to be some various forms of gradient descent. And there are also second order methods which use the curvature. So this is the second derivative. It's not that easily making visible. I cannot easily make this visible here in this parabola example. Although if you have some more advanced optimization problems, these second order methods can be beneficial, but we will also see some limitations of them. So usually you don't use second order methods when you are in deep learning problems, and there's a couple of reasons we will address later. Oftentimes the methods of choice are those involving first order, since we can easily obtain gradients. As we will see, tomorrow we will look at something that is called automatic differentiation, which is a super handy tool in order to obtain gradients out of programs written in Python. This is kind of the first big distinguishing factors. And the second big distinguishing factors is, so this is more like on the algorithm side. And this is then more on the, or actually what follows is more on the problem itself. So usually in optimization, one distinguishes not necessarily between linear and nonlinear optimization problems. So problems which have nonlinear or linear functions, but rather problems which are convex and non-convex. And the big point here, maybe from a really practical perspective, convex optimization problems are way better behaved. So many things that there's a lot more theory in mathematics and a lot more, way better developed algorithms to perform convex optimization. And there are also really good examples of convex optimization problems. that you also find in machine learning. But for instance, if you want to do deep learning, artificial neural networks, or the training of artificial neural networks usually is a non-convex optimization. And non-convex optimization usually has the problem that we run into local optima. And local optima means that if you have functions that, for instance, look like this, they kind of give you, so if you were to follow the gradient, you would end up in a minimum. Of course, it's a minimum and by a mathematical definition, but it's not a global minimum. So you would rather be interested in finding this minimum. So in an optimization problem where this, for instance, would be the cost, and this is some certain parameter that you can tune, then you might rather be interested in, so cost also in terms of money, then you might probably be interested in having a solution which costs less than one that is more costly, although both being minima. One is the global minimum, and you try to find not necessarily the global minimum, but you find minima that are at least quite close to what the global minimum is. Then we also have a big category which is on constraints. Constraint optimization is, I mean, in the first it kind of seems a little bit, it's kind of a realistic thing though, as you will have it also in many problems in real life where you try to perform optimization. The thing that we looked here that we looked at here in our super simple example is a so-called unconstrained optimization. So we are trying to find the minimum of the function over all possible values of x. And so this is kind of going, x could be any value from -infinity to +infinity, and we try to find its value where it is minimal, or where the function value is minimal for. You could potentially also say, well, I only want to find x's for which the x coordinate is greater than, let's say, 0.2. And then your minimum of the optimization problem is no longer at x equals 0, but it is rather at x equals 0.2, because that's the lowest value. And of course, it's a super simple example here. And these constraints can be rather complicated, but usually from a practical perspective, if you're unconstrained, this is the easiest thing you can have. Equality constraints, so this basically refers to that the x's need to have a certain value. This will make sense in higher dimensions, are almost as on the same difficulty level as unconstrained optimization problems. However, inequality constrained optimization problems. And inequality constraint is referring to this x has to be greater equal than 0.2, because this is an inequality here. That's why it's called inequality constraint. They turn out to be rather more difficult. And on top of that, just some general mathematical consideration is like smoothness, continuity, but this also greatly affects, of course, the difficulty and the choice of algorithm. But for my personal usages, this is kind of the most distinguishing factors if you want to really broadly categorize optimization. Okay, so the reason I bring this up now is that we kind of want to translate this somehow into the interface SciPy has chosen for its optimized functions. And for this, I took a screenshot of the documentation. It's better if we maybe take a look at it ourselves. Okay, well, that's the link is a little bit outdated. So let's see if we can find documentation ourselves. No, we can't. So let's see. So we have scipy.org, and we want to go to the SciPy reference guide, I think. Exactly. So then we want to go to the optimization and root finding. And so we looked at the minimized scalar function. I mean, there are also a lot of interesting scalar optimization problems, and scalar is referred to that the input x, or the design variable over which we are optimizing, is scalar valued. And that was the x in the simple example. For more interesting optimizations are, of course, multivariate. So this refers to x being high dimensional. So it could be only 2-dimensional, but usually it's dimensional in the range of 100, 1,000, millions, billions even. And there we want to look into this minimize. And now I want to dissect kind of the interface with you a little bit. So the minimize is a call to, say, to minimize a scalar function of one or more variables. And it takes a function. Well, this is the objective, the target function. Well, then it takes an x0. This is kind of an initial guess, starting at which we want to start our optimization. And those iterative algorithms that optimize functions, or minimize in that case, they tend to be really sensitive to the initial condition. So it might be reasonable to have solutions or initial conditions which are already close to where we expect the optimum to lie. Then, really important, there is an argument which is called method. And this method is by default none. And here we see method is a string or a callable. I mean, this is the type it is expecting. So recall the colon afterwards. And it says it's optional, and it should be one of those. And here you see all the algorithm SciPy supports, at least in this recent version. I think it's the most recent one, yes. And I don't want to go into the algorithms in too much detail, but I believe that this is kind of, in most regards, matching what you find also in MATLAB. I think there is a function called fmin and fmin_con for constraint optimization, and this should kind of match what the function should match the functionality you have there, at least for small and medium scale optimization problems. And then what we also find here is a JAG, which stands for Jacobian, and a Jacobian is usually just a Jacobian is just a generalization of gradients, and this is kind of a way in order to hand over a function which, given a coordinate, not just prints out the value of that function, but the gradient. So just to give you a little bit of a perspective on that. So in case you are looking at the paraboloid again that we drew in this 3 dimensions, so x, y, and z, and then we had our paraboloid, if you remember, something like this. And the objective function, so the function we have to hand over, is kind of this function which is given a point x, is given us the function value, so f of x. And then we can hand over a function which gives us the gradient. So this is a gradient, so this would be gradient f of x. And then Python or SciPy can work with that and can hand it over to these lower level implementations, like the implementations in C, Fortran, and so on. Although I think this minimize is to some extent implemented, at least the control structure is implemented in Python, but I could be wrong about that. And Hessian is a way to hand over the Hessian for this second order methods. Then we have bounds and constraints. So from a practical perspective, SciPy differentiates between bounds and constraints. So because we have bounds, which are kind of easy inequality constraints, this is the one that I showed to you where you say, well, x has to be greater than 0.2. That's a bounds constraint, but we could also have more complicated constraints. We could, for instance, have a constraint which reads something like x to the power of 3 minus sine of x has to be 0.8. Or has to be smaller or equals 0.8. And that's how, this would be a really ridiculously hard constraint, but I think you get the point that it's not just a bound. So it's not just a box on the axis, but it is rather something that is way more complicated. And then there's some more options like on the tolerance of the solver, some callbacks and further options. But really interesting for us is how they chose to do the interface. So the target function, initial guess, then the method, the Jacobian, aka the gradient, and the bounds and constraints. And you also see that here. So Jacobian says method for computing the gradient vector, and it says it only works for a couple of algorithms. That's of course because only a handful of algorithms are first order or second order, in that they can digest gradient information. And you also see how the function signature should look like, and especially also with respect to what shapes the array have, and so on and so forth. So Hessian, I think I told that to you with the bounds and the constraints. Okay, let's just start with a super simple example, and then we will add some small constraints. So let's hand over to VS Code session. And now I want to implement a more complicated function. So here in that case, I want to do f, let's say, paraboloid. And for this, I want to use lambda x and then say x0 raised to the power of 2 plus x1 raised to the power of 2. And so we haven't seen that yet, but here I assume that x is a vector or a one-dimensional array. So I couldn't just call this function with a scalar. So if I were to call this function, let's say at point 2.0, it says float object is not subscriptable. And that's of course because, a float is not a vector, or a scalar is not a vector. But I can easily call it. For this, I first have to import NumPy. And let's say, for instance, x point is going to be np.array 1.5, 1.5. And then if I call the paraboloid function on x point, then it will work. So here I said I just have the paraboloid, and this of course has its minimum at 0, 0. And now we want to find that minimum using the optimize minimize function. So optimize, just bring that over here, just in case you have a question. Oh yeah, okay. There's someone asking, can you please explain convex optimization again? I will come back to that in a second. Don't worry. Then we have optimize.minimize, and then plug in f paraboloid, as well as an initial condition, so not an initial condition, but an initial guess for our optimization. And then, for instance, we take x point. I mean, this is just a point here. And then it says, well, it has found a minimum. So I think it says, yeah, success equals true. And it has found the minimum at minus 4.3 times 10 to the minus 9. And this is a really small number, which of course refers to that it's almost 0. The analytical optimum would be at 0, 0, but here it has found a value that's close to that. It also says optimization terminated successfully. And the reason it hasn't found like 0, 0 is that it is like running until a certain tolerance, because often, of course, the really exact optimum is not really relevant. Of course, this kind of depends on the tolerance you choose, but often it is just reasonable to just be close to the global to the optimum. And we see some more statistics. We see the number of function evaluations, the number of optimization evaluations. You see the number of Jacobian evaluations, and the status is just like a flag here. And the reason this is relevant, why it is presented to us, because optimizations are an extremely, extremely expensive operation. For instance, imagine you perform a simulation, for instance, including computational fluid dynamics. And every time you perform the computational fluid dynamics simulation, you then evaluate the results to turn out into your target function. So for instance, you change a certain parameter in your geometry, and this then results in a slightly different drag or lift coefficient. And you now might be interested in minimizing those. And every time you evaluate your simulation, every time you want to perform an optimization iteration, you have to at least evaluate your simulation once. And if your CFD simulation runs for 10 hours, because it's a tough simulation, or even more, or might be less, then you might want to have as few evaluations as possible. So it can be kind of helpful to get a feeling for optimization problems and optimization algorithms in order to choose the right tool for the right moment. And because the difference between an optimization which takes 15 or 20 iterations and an optimization which takes 10,000 iterations can be also the question whether the optimization is feasible in the first place, and if you want to use it at all. Okay, before I come to the bounds-based multivariate optimization, I want to explain the convex one once again. I mean, of course, this is kind of a loose definition. There's definitely a precise mathematical definition. To have a convex optimization problem, you need to have a convex target function, and you need to have convex constraints. But let's just consider a convex target function for a second. And convexity in the mathematical sense, at least in 1D, we can find it like this. So let me give you an example of a convex function. This would, for instance, be the parabola. And convexity means that when you take 2 points on the function and you draw a line in between them, this line does not intersect with the function at another point. So here in that case, I kind of have to imagine these points moving. If I had this point and this point, so if I move them to arbitrary position, at no point in time, this line would intersect with the parabola. And let's just give you an example where this would be the case, where we have, for instance, something when we have the cubic function. And if I take this point and draw a line between, this kind of intersects with the function here. And this kind of makes the cubic function non-convex. This is, of course, a little bit theoretical. I mean, from a really practical perspective, the definition of non-convex and convex, at least how I remember, is that if you have convex optimization problems, the local minimum is the global minimum. So this means that the minimum that you find with your optimization algorithm is the global minimum. That means, for instance, if you can assure that your optimization problem is convex and your optimization converges and you find a minimum, then you know there is no other point which is better than that. Whereas if you have a non-convex optimization and you find a minimum, you can't be sure. And on top of that, convex optimization problems are easier to solve than non-convex, because there are certain algorithms which can take advantage of the properties of convexity. Okay, I hope that answered the question. If that did not, please ask a follow-up question. I think this can be a little bit abstract, because I think this is something that is not usually taught in engineering math courses, but I think it's kind of nice to have like a little bit of the background to know what you're heading for. Realistically, this is an extremely deep mathematical topic. You can probably spend years in studying that, but here we're just interested in it from a practical perspective. And we want to kind of see that how the mathematical world translates into an interface of SciPy. Okay, I will take that question. Again, please ask a follow-up question in case something is unclear. Now we want to introduce some bounds into our optimization problem. So let's head over to Visual Studio Code again, and let me put away my drawing tablet. And we now want to put a bound on we want to put a bound on our x, basically. So what we do is we say optimize optimize dot minimize, and then we have our f paraboloid again. We start at x point, and then I want to use bounds. And then we have to select how we want to hand over the bounds. And here I want to say that I want to bound the different axes, and I want to bound them in the following way. So I want to first, so we will be having a list of bounds. So that's why I'm using the square brackets. And then we define the bounds by regular brackets. And I want to bound between 1 and 2 and 1 and 2. And if we then run this optimization, we see that our optimum value is at 1, 1. So basically what we did here is we said that the first axis of our optimization, the first dimension of x shall be bound between 1 and 2. So x is only allowed to take values between 1 and 2. So 1 smaller equal x smaller equal 2. 1 smaller equal x0 smaller equal 2. And then we also have 1 smaller equal x1 smaller equal 2. And if you look closely, you kind of see that the optimization printout that we get is a little different. So first of all, we get a message here. It says optimization terminated successfully, and it's written in a properly capitalized way. And here it kind of screams at us saying a convergence, norm of projected gradient smaller than PG taller. The reason for this is that in the bounds, in the bounded optimization problem, SciPy using a different algorithm. And in that particular case, I don't want to say something wrong, but I'm pretty sure that this is kind of a third-party library. And this optimization library kind of also gives you convergence messages, and it's just like literally the string taken from that library, and that's why it's not that well formatted. So either way, kind of SciPy does a lot of magic for you behind the scenes, so you don't really have to think about optimization methods. And on top of that, something really nice, SciPy is also approximating gradients and, if necessary, also Hessian information for you by finite differences. So in case, so as you see here, we didn't provide the Jacobian. I mean, we could. Let's just provide the Jacobian. So maybe that's the example of the bounds. So maybe let's provide the Jacobian explicitly and say that so again, f of vector x is or was x0 squared plus x1 squared. And now we want to take the Jacobian the gradient in that case. So the gradient of that function would be a two-dimensional vector, and it would here be 2x0 and here 2x1, and this is a two-dimensional vector. So here the target function is, so this one is scalar valued, and this one is a two-dimensional vector. So let's define a function. So I've seen a question on Slido. I'll get to it in a second. So let's define a function that computes the gradient. So let's say, for instance, I want to have a function, call it gradient, and we will again use the lambda structure here and say it should return a NumPy array, which first entry is 2 times x0 and its second entry is 2 times x1. Okay, this was a little bit quick. Let me just explain it again. So it takes x, and we assume x is going to be a NumPy array, a two-dimensional NumPy array. And then we say that the gradient is given as 2 times x0, so or x, depending on how you want to call it, and 2 times x1, or y if you want to call it. So for instance, if we have our x point, so this is the position we're at, then the function value, is going to be f paraboloid evaluated at x point, and the gradient is going to be, so it's given if we evaluate the gradient function at x point, and it's going to be a vector. So at position 1.5 and 1.5, our paraboloid has the value 4.5, and at that position it also has the gradient, which is pointing in a direction 3, 3. And then we could feed our optimization problem with the Jacobian function. And here, let's say this is, oh no, this was incorrect. So we should go a little bit more up. So yeah, and here we should have Jacobian is gradient. And here we go. So if you then look at the optimization result, they are again different. That's interesting. So here we see that we have the same number of iterations. We have the same number of Jacobian evaluations, but we have a different number of function evaluations. It seems that here in that particular case, the SciPy optimize is using the same optimization algorithm. I mean, we get the same convergence message that kind of screams at us. And the reason we have fewer function evaluations is because SciPy, or the optimization algorithm, does not have to approximate the gradient, because we explicitly provided it with a function to compute the gradient. Okay, let me now refer to the question on Slido. So there was, what are these terms? For example, NFEV, NIT, and so on and so forth. So, okay, great. I just repeat it once again. So NFEV stands for number of function evaluations, and NIT stands for number of iterations, and NGAV is number of Jacobian evaluations. And that kind of gives you an understanding how costly your optimization was, costly in the sense of computational cost. I mean, in this super contrived example, you can't even speak of computational cost, but once you have like really tough optimization problems, it might be interesting, or not interesting, it might be relevant to investigate those kind of metrics. So then I would tick the questions on Slido, and then I would return to the slides and just give you some super simple advice here. Some typical pitfalls in numerical optimization. I already mentioned that if you have a non-convex optimization, which is quite common in deep learning, local and global optima might not coincide. And the key point here is, and that's also what we will see later on, tomorrow when we look at deep learning, often a good local optimum is sufficient. Meaning that if you find a local optimum that defines a machine learning model in a sense that it's good in the metrics you came up with and it's generalized as well, then this is often a better choice than having a poor global optimum. Poor in certain senses we will also look at in the machine learning section. Often also methods are unable to converge. This can have multiple reasons. And of course, the more complicated your problem is, so also including non-convexity and non-linearity, methods might have a hard time. And initial conditions or initial points are crucial. And of course, all the other constraints that you face when doing scientific computing, like not having enough memory, and of course that certain problems might be badly behaved. So there's a lot of things that could go wrong. Luckily for us, at least, the SciPy interface tries to circumvent a couple of the more obvious mistakes one can make. So for instance, choosing a wrong algorithm for a particular problem. So for instance, choosing an algorithm that only works for convex problems, for non-convex problems, but in the end, one still has to probably iterate a little bit over that. And then one really, really important point here, when we then later on look at machine learning, is that the machine learning is it can be tricky to understand, but machine learning, when we see it, is a way of optimizing over parameters. And you kind of have to think of that as a machine. So maybe what is a good idea? But if you imagine a big production plant, and this production plant has maybe I don't know. Let's see. For instance, let's just use a black box structure, and this production plant takes in some X, which could, for instance, be some raw materials, that could be crane, that could be whatever it might be, and it returns some output Y. So it takes some input, outputs Y. So this is like a typical procedure, any kind of function. And inside of this factory, there are a lot of tunable knobs. So for instance, the temperature at which a certain reactor is running, the speed at which certain pumps are running. And you can think of different units. So for instance, what would be a good unit for the speed of a conveyor belt or something like this. And machine learning is an optimization over these knobs. I mean, right now we looked at the simple parabola function, which only have an input X and an output Y. There we optimized the optimal input, but in machine learning, we're rather interested in the optimal knobs, so the optimal tunable parameters. I mean, we don't have to explicitly, we're not looking into that much detail that we would have to code that in Python, but I just wanted to make you aware of that because what I've shown so far could have led to some wrong conclusion. There's a question on Slido saying, is there an algorithm to choose the best initial point? Well, I mean, probably there is, and probably you can think of something how you could do that. But oftentimes finding the best initial point is harder than solving the problem with a bad initial point, if that makes sense. And in the end, the best initial point is to be already at the minimum. So it's kind of a balance that you have to make there. Oftentimes, especially also with respect to deep learning, the initial point is chosen randomly. And then there are some mathematical analyses which kind of give guarantees that if we choose it randomly in a certain way, we randomly have better convergence properties. It's really abstract, but in the end, it's kind of a science for itself. But the takeaway, I think, is just that it can have a big influence. I hope that answered the question. If not, please ask a follow-up question. I will tick it off. Great. Let's move on to a next point in SciPy I want to show to you, which is, I want to call the world of distributions. And the second aspect, which machine learning is based upon, as we will not see that after this example in SciPy, because we will rather look at it from a practical perspective. But many of the machine learning algorithms are based on probability theory and statistics. And this can be an intimidating field, especially, I think, since engineering courses usually don't consist of those kind of mathematical disciplines. But I just wanted to give a brief overview that SciPy also has the functionality required for that. So for this, let us hand over to VS Code again. And this time I will first clear the screen with Control L, and then I want to import the stats package. So from SciPy, import stats, and stats stands for statistics. And then if we look at stats dot and just give us the auto completion, we are kind of overwhelmed probably. So if we take the arrows to kind of move around here a little bit, you kind of see that there's so much functionality. And the reason there's so much functionality is just because there are so many different distributions. And distributions are kind of a way in order to express randomness or express probability. And yesterday with NumPy, we've already seen uniform distributions and normal distributions. This is also probably the more well-known ones, but you also find many, many other stuff. And here I just want to look at normal distributions because the rest of the stuff is probably only relevant for you if you really want to dig deep in that or want to do some statistical analysis. So let's look at a normal distribution. And let me introduce the example I want to give to you. So let me hand over here and let's see. So here we have that. So the thing I want to show to you is kind of something that you might have observed in some exams that you have taken in your undergraduate or graduate education, which is that if we have the grade of an exam here, and in the German grading scheme, you have 1.0, maybe then a 1.3, 1.7, 2.0, 2.3, 2.7, 3.0, 3.3, 3.7, 4.0. I think you get the point. And if you then draw a bar chart in this, in kind of like these grades, you might see a distribution something like this. So, I mean, it depends on the grade, depends on the exam. Maybe that's, I don't know. This is probably not thermodynamics. I don't know. This kind of depends. I haven't seen the statistics in recent years, but I think you get the point. So there's like a distribution. Some grades are seen more often, some are less often, and often you have kind of this peak, depending on how easy the exam was, somewhere around 2.0. In a good approximation, this can be a normal distribution. So a normal distribution kind of looks like this. It has this bell shape, and the reason I say in a really good approximation is that the normal distribution is defined for values all the way to -infinity and to +infinity. However, here we are only looking at values in between 1 and 4. So let's take it with a grain of salt, but I think it's just a little bit to give you the big picture on distributions. Okay, so let's head over to our VS Code session and instantiate a random variable by saying grade. So the grade is the random variable, and say this is stats.norm for a normal distribution. And then a normal distribution is defined by 2 parameters. It takes a mean, so a center, and a standard deviation. Let's say, for instance, our exam is centered around the grade 2.2 and has a standard deviation of 0.6. Then we can take a look at grade. And we see it's a frozen random variable. That's kind of a little bit abstract here. And we can then use this grade random variable in order to perform various statistical or various tasks in statistics. So for instance, we can sample the random variable. Sampling refers to drawing random numbers that adhere to the probability density that this distribution defines. In the case of our example for crates, it would refer to crates that are given in accordance to this normal distribution. So for instance, crate.rvs, and RVS stands for random variates, I think. So in the end, it's just a sampling. And then we say how many samples, and we want 10 samples. So here it gave it 10 different crates. And of course, you see one crate that does not work. I mean, this is a crate better than 1.0, but this was, of course, due to the fact that we used this super rough approximation of the normal distribution in this particular scenario. And we can try it again, and then we'll get a different number. And then there are many other activities that you might be interested in using random variables for. So for instance, you would want to query the probability density function. So how high is the probability density to obtain the crate 2.0? 0.62. I mean, this is not a probability, it's a probability density, but we can also investigate the probability by examining the cumulative density function, CDF. In essence, this is the area under the curve. And this works as following. We can say crate.cdf and then say 2.5. And that would basically refer to, it should be CDF. And that would basically refer to how high is the probability to get a crate that is better than 2.5. So it's lower than 2.5. And that's 70%. So this one is a probability. And in the contrary, that means, of course, that the probability of getting a crate that is worse than 2.5 is the complement to that, which would be about 30%. And of course, there's many other functionality. I don't want to dig deeper into that. And I just wanted to give you the highlight here that you can do a lot of things with respect to statistical distributions. Then I will head over to the slides again, and I have a small quiz for you. I mean, not a quiz, it's rather, I want to poll your opinion. And so, so we looked at these stats here, and the question is the following. I mean, it's the typical probability thingy. So you say you have a coin, and you flip the coin 100 times. So this is a typical coin, a euro coin, for instance, and it lands on head 57 times. Question, is that suspicious? 71% think no, 14% say yes, and 14% say it depends. I think all of you are kind of right, but it's kind of something that I want to head forward to. Maybe let's rephrase the question and let's say, what happens? What do you think if it lands head 70 times? Let's maybe reset the poll. What is your opinion on that? Now it shifted towards yes. Again, I think every answer is correct in that sense. The reason I bring this up is because we want to do some super simple statistical test here. Of course, it's hard to say what is meant by suspicious, but here the idea is that we will do something that's called a binomial test. And it kind of aligns with the idea of what a statistical test is. And I just want to give you like a super simple, rough definition of what we're going to do. Is in a statistical test, one has to define a null hypothesis. It's often called as H0. And in a hypothesis, in that sense, is just a statement. And often the null hypothesis is chosen in a way that everything is okay. So nothing is super extraordinary. In that case, it would mean the coin is not biased, because we would expect the coin to be perfect. So why should it be biased? It's rather unlikely to have a biased coin. In case it is made perfectly, the coin is rather unbiased and should land head and tails equally. And then we have an alternative hypothesis, which says that the coin is biased. So because it lands on one set, or on one outcome is more likely than the other. And kind of what a statistical test does, or a hypothesis test in that sense, is we try to find the probability of the null hypothesis. So we want to know how likely it is that the null hypothesis is correct. No, we want to try to find how likely the null hypothesis is. So given the circumstances, how likely is the null hypothesis? And if the probability of this null hypothesis is below a certain threshold, we reject the null hypothesis, because we then say, well, it's so unlikely, it's so improbable, we will rather not accept it and rather choose the alternative. I mean, in the end, we can't really say whether it is really true or whether it is false. We can only say we're kind of certain that it's not right. So we rather reject it. In the end, this threshold level to say upon which we say, okay, no, it's hard to trust, we should do something else, is of course a little bit subjective, but this is kind of what empirical sciences usually struggle with. Either way, let's just try to perform that. And for this, let's go over to Visual Studio Code, clear the screen. We will use the stats packet again. And let us first define the number of total observations. So this one is 100. Then we have the number of heads, which shall be 57. And then we have the head probability expected. And this is just a translation of having a fair coin. So a fair coin is kind of defined by having equal probability for head and tails. So this one would be 0.5. So it is equally likely that it lands on head or it lands on tail. And then we do a stats.binomial test. And this one just takes the number of head, the total number of rows, and the head probability expected. And then it spits out a number. So maybe we try to access that and say that this is the binomial test result. And the binomial test result consists of, a so-called p-value. Ah, yes, of course. I did that wrong. Unfortunately, sorry, there should be, this is without an underscore. So that's kind of like a legacy feature that it was some time when SciPy's interface was called with an underscore, and apparently they now favor the not underscore way. And now it should work exactly. So this is a binomial test result, and there's a couple of results estimates here, but we are interested in the p-value, and the p-value is the probability of the null hypothesis. And again, say the null hypothesis was that the coin is not biased. So because this is the everything is usual and nothing is special hypothesis. If you have some real-world examples, is that you have, for instance, you want to test the efficacy of medicine or of vaccines, then your null hypothesis is it does not work. So everything is as usual. So it does not have an effect. In our case, is nothing is special. Nothing, the coin is as usual. And this is kind of 20% approximately. And usual thresholds, so usual thresholds are, so I think empirical sciences usually use a 5% threshold. Oh, of course, there should be a comment, I'm sorry. Usually empirical sciences use 5%. And since we are above 5%, we don't reject. So we believe that the coin is not biased. And of course, if we were to do a binomial test at a higher count, so binomial test, number of heads, let it be 70. And then access the p-value. And then here we get 7.8 times 10 to the minus 5, and that is definitely smaller than 5%. So here, when we have 70 times head out of 100 rows, there's the chance that this could actually happen in that particular way with a fair coin is really low. Therefore, we would rather say the coin is biased. But of course, I mean, in the end, it could be not biased, and it's just a rare event. But it's in the end how probability and statistics work. Great. I hope this kind of a small tour into the world of statistics with SciPy was interesting for you. Let's head over to the slides, and I just want to quickly summarize that. the bottom line here for me or for you should be that there's a lot of functionality in SciPy. Maybe the examples I chose here are rather contrived, but there's a lot of things where you can use it for real examples, for real world examples. So we looked at the statistical tests here. Maybe let's quickly poll whether you've used that before. Has it ever been useful for you? Maybe excluding courses in your undergraduate or graduate studies. So let me reset the poll. What do you think? Have you ever used that before? Yes, no. I mean, there shouldn't be an answer. It depends. But if you want to answer it depends, feel free to answer it depends. Yeah, cool. Nice that the majority. Yeah, we have the it depends answer. That's also the right answer whenever talking about the probability or statistics. Have you ever used statistical tests before? It depends. Great. It's interesting that the majority of you used it before. The last time we polled that with the last two workshops, we actually had the majority voting for no, which is interesting. So then it's cool that you've seen that, and this is you can do that here. Certainly, of course, if you are rather used to, for instance, SPSS or other statistical software, there's a good chance that it might not have that nice of an interface. But the advantage of Python again, and that's kind of what I also want to emphasize on, that you have this functionality in the scripting language and can therefore easily access it within many other computations. So for instance, you write an ODE solver, for instance. I mean, it's a terrible example, but let's say you have an ODE solver and use SciPy in order to solve it, and then you make some statistical analysis based on the results that you get out, but then you perform some optimization, and you can glue all of that together in Python, and you might not even have to just use SciPy. There are also other libraries for which you can use statistical programming. So for instance, Stan, which is a really, or Stan or PyMC3. And that is, I mean, what I think is the big power of Python there. Well, then I think we skip the next statistical test. It's not too interesting. And then I want to quickly go over the SciPy documentation one last time, and then I will give you a small break, and then we continue with the machine learning section of the workshop. SciPy optimize. So maybe it's just me, but I'm also sometimes a little bit weird. I really like to go over these documentations because I think there's so much value to gain from just seeing how other people try to solve software problems. And I also like to see interfaces, because interfaces, especially in software, kind of also give you a really practical perspective on a lot of numerical algorithms, because in these interfaces, you always see how to think about these algorithms on a high level. Because when you tend to learn them in your education, or you read a book about them, you have this theoretical perspective, which is of course not bad, but you tend to not have the bigger picture in that sense. And that's what you get from looking at the documentations from time to time. So let's, for instance, look into the integration and ODEs, just to show you that is there. So we have quadrature functions. Let's ignore quadrature for a second and go to solving initial value problems. And in SciPy, I think this was like now almost 10 years ago, they introduced a new interface, which is called Solve IVP. And here, this is kind of a general interface to an ODE solver. And similar to what we have with the optimization, we are providing a function which is computing the right-hand side. We have an integration horizon. We have an initial condition. We choose a method. So here by default, it's using the RK45 with the dope pre-weights and some more options. And it's so cool. And I think it's like it's an amazing thing that all these stuff is so well documented. I mean, of course, there's a lot of points where it could be better documented and it could always take more examples, but just the fact that it's like freely available and has this amazing documentation, this is kind of often restoring my faith in humanity, that there's like a collection of enthusiasts who over years kind of built these freely accessible tools, and they've been proven and used in a lot of research. And in the bottom, I don't know if it's also here, but often you find examples. Yes, you find examples here. I mean, you find a lot of references as well. but you also find examples from which you can take inspiration. Sometimes the examples they have on the SciPy documentation are a little bit advanced. So often it's better if you just Google for some examples and you find tutorials like giving you intros. And yeah, so there's a lot of things to do. And also look over the other libraries. I just can highly recommend it. Okay, that's it for the SciPy section. Okay, welcome back. Let's now lose all the stuff we learned over the last day and also over today to finally go into some machine learning. And therefore I will share my screen again. Here we go. Okay, let's head over to, let's skip this statistical test and head over to Scikit-learn. And first, let me give you like my extremely rough definition of machine learning. So in my perspective, machine learning is a combination of data, statistics, and probability theory and optimization. That's why we also looked at that in the case of SciPy. In our particular case, we will not be considering optimization in too much detail, and we will also mostly leave out the statistics and probability theory part. Crucial, of course, is the data part, since we kind of need to know something that we can learn from. And then basically what machine learning tries to do is to optimize, so in a sense of finding optimal values for certain adjustable knobs or adjustable values of a parameterized model to data. And key is parameterized model. And not, of course, I didn't want to like strike that through, but the parameterized model is the key idea here. And also the idea of model. I mean, as we have models also in physics, there are some models in machine learning. They have certain assumptions and they might work well in certain situations and might work not so well in others. What are different tasks in machine learning? So this is just like a super rough overview to give you a perspective if you've never heard that before. Typically one distinguishes between supervised and unsupervised learning. So supervised learning is, let's say, for instance, earlier we talked about the example of this factory where you had something X and you have something Y, and you want to learn the optimal way to go from X to Y. And in order to learn that, you are given some examples of both X and Y. And this would be supervised because you are first given where you start from, and then you're also given where you want to be at. So it's supervised because you know what is the right thing to do. Unsupervised, on the other hand, would just mean you only have access to the input. I mean, it's kind of a little bit confusing because there are also applications where there is no clear why, but usually an unsupervised example is just that you only know the input and you have to make sense of that. Supervised, I mean, for most applications that I'm aware of, supervised learning is always the learning of some sort of a mapping or a function. And this learning for mapping of functions then, for instance, means I give you, like the classical example you at least have heard of once, I give you a picture of a cat or a dog, and you tell me whether it is a cat or a dog. And you have been trained on a couple of images, which I told you, this is a dog, this is a cat, and then you learned over time. Unsupervised would, for instance, mean I give you a bunch of images with dogs and cats. I don't tell you which is which, and you're supposed to figure out certain intricacies. So for instance, there are certain similarities between pictures that contain dogs. So for instance, because dogs tend to have different body postures, or I mean, you can think of many things that distinguishes dogs and cats. And it's unsupervised because I don't give you the relation that you should be finding. So I don't give you like input-output pairs, but only some input. And then one usually distinguishes between regression and classification. And regression basically means that the function mapping that we're doing is towards a real valued number, and classification is towards a discrete set of classes. So the case of cats and dogs would be a classification. So because an image should be assigned either the label cat or either the label dog. Regression problems are usually, I think, For many scientific machine learning applications, I think regression is the more used. It is kind of learning a function. So let's say, for instance, you are given only an x and y, one-dimensional x, one-dimensional y, and you give it this kind of points. Let's say that's a lot of points, and you're supposed to learn the relation between that. And this is then kind of a regression function. And you want this because you then want to query new values at new positions. And you then, for instance, often find this in control problems where you might want to learn control laws given some sort of deficits. How do we have to steer certain aspects of a control system in order to get into the state I want? And then, of course, this is a little bit more of a theoretical and internal perspective, but I think it's interesting to look at and to kind of be aware of that. I mean, as said, you don't have to be experts in optimization. You don't have to be experts in statistics to practically use that, but it's nice to have that in the background. So as said, often machine learning is an optimization problem, and therefore it comes with all the difficulties that optimization problems are. So it can be convex, non-convex, and we might have problems where we find closed form solutions and sometimes where we need iterative approximations. So this basically means when we looked at the example of finding the minimum of this f of x function, which was x squared, we could have also done this analytically, or we could have also just guessed it. But for a lot of problems, we can't find analytic solutions, and then we have to resort to iterative approximations. Okay, that's just as a quick overview. I wanted to introduce that here, such that we can then later on classify the techniques that I want to show to you. Okay, some practical considerations of machine learning. So a lot of the machine learning is actually about knowing your data. So get as much prior knowledge as possible. In the end, I mean, we're looking at some contrived examples here. So the data that I'm presenting to you for the tasks we're solving today and tomorrow, it's first of all, either it's artificial or it's already like well-behaved. And in real life, and also in scientific machine learning, way of science, scientific applications, data is noisy, data is imperfect, data might miss certain aspects, and often you spend a lot of time in cleaning and pre-processing the data, and this shouldn't be underestimated. Whenever you, for instance, tasked with performing any kind of machine learning, it is relevant to be aware of this, that this can easily take the most of your time. And equally relevant to knowing your data is also knowing your tasks, so that you kind of know how to assess a model. It's the same for machine learning modeling as it is for a physical model. Models will always be bad, but some models are useful. So you have to be aware how you measure usefulness. And if this is a model that you were looking for, that is kind of assisting you in the problem that you had to solve initially, then this is, of course, a metric you somehow have to express. And then we will also use that later on, is to divide your data set, or whatever kind of data metric data you have available, into a train, validate, and test subset. This will become clear in a second, but it's also kind of obvious that if you take an exam in uni, they don't ask you the questions that they did in the exercise, right? So in other words, we want to avoid that machine learning models learn the data by heart. And this by heart learning is called overfitting. So we want to avoid overfitting. The best machine learning model is this one that is generalizable, so it has learned the gist and can then apply it to unseen data and perform well. So this is something that's kind of like of practical relevance. And then something that's really close to the bottom of my heart is that you should rather prefer simple solutions over complicated ones. And I've taught that a couple of times. Often one tends to prematurely optimize, and also one tends to favor fancy models. And especially if there's a lot of hype around, for instance, around machine learning and deep learning, one tends to copy the trends and keep on neural networks, but a lot of problems, and I hope I can convince you of that with the Scikit-learn chapter, is already solvable by simple techniques, in that case, linear regression. And we will then see how we can make linear regression more powerful. And I think in particular for scientific applications, because already earlier I mentioned that there is kind of this hybrid between using machine learning or some sort of data science plus the original models that you have. So for instance, your Navier-Stokes equations, your other kind of descriptions, or mechanical laws like Newton's law of mechanics. And having this kind of knowledge and combining it with a little bit of a nice linear regression model or some other kind of simple model. It can also be a neural network. It can be a small neural network. Can then improve a lot of the performance, but is still kind of interpretable and generalizable. And this is in machine learning, this is often referred to as so-called Occam's razor. Occam, I think he was a monk, if I read that correctly. And basically, in plain English, it kind of says that you should favor simple solutions over complicated ones. I would like to poll from you if you have ever used machine learning before. Okay, let me bring over the results. So 22 votes so far, and we have a majority on yes, although it's not by a large amount. Of course, one always has to say, where does machine learning begin and where does machine learning end? So we will mostly look at simple examples, especially with respect to like linear regression. So I'm pretty sure linear regression is something that is done quite often. I mean, not everyone has done it before, but it's something that is a rather really simple and straightforward machine learning algorithm. And usually then sometimes we might have not done some more advanced things, but still that's a good amount. And I hope I can still show you the intricacies of scikit-learn. And this will also be a good exercise to that kind of combines all the knowledge we have gained so far. So we will be using Python data structures. We will be using NumPy arrays. We will be plotting our results. Probably I have to improvise and switch to Plotly and can't use Matplotlib here due to the issues we had earlier. And of course, we will also use SciPy at a certain point. So this kind of is bringing it all together. One last point before we start with the linear regression. I want to talk a little bit about the package we're going to use. So it's going to be scikit-learn. And I love scikit-learn. I think when I started using scikit-learn about 3 years ago, it is kind of like there's so much value I gained from using scikit-learn, since it's an amazing package with regard to its API design and also with respect to the documentation it has. So let me open up the documentation for scikit-learn for a second, so that we can take a look at it together. I mean, not in detail, but I would just highly recommend it. So they kind of have these types here, first with user guide and then API, and I'm here on the user guide, and they document all their kind of algorithms in really, really great detail. So we will look at some supervised learning today, and then they have a lot of different subsections. I mean, probably you can spend hours reading that, but it has so much value in there, especially because it is accompanied by really good coding examples. And I tend to learn better when I also see the coding right away. It's at least also what I hope to convey here with the workshop. Okay, enough fancy talk about scikit-learn. Let's go to the slides again and start with linear regression, probably the simplest thing you can do in machine learning. And in our in our categorization, linear regression is going to be a supervised technique. So we will have this XY samples. It is a regression. I mean, it has it in the name. And this is really good. And I mean, we won't see it like explicitly, but it is a technique with a closed form solution of a convex optimization problem. So it is perfect, easy in that sense. And I'm pretty sure you've seen that before. We have some sort of scattered points, and these points form a linear dependency. So we see some proportionality in there, and then we can attempt to find the line which best fits these point in that sense. And often one tends to think of these best fit in that we have little springs. So if there are little springs from the point to the line that we want to find, so I hope this makes sense to you, and the linear regression that we're going to find balances all the springs. So it's kind of finding the, I mean, loosely speaking, the equilibrium of these springs, such that we have an optimal line with respect to the points. Okay, for this we will look at an example data set from the Scikit-learn, So let's head over to VS Code and write a script for a simple linear regression. VS Code, let's close that down here. So make it smaller, the terminal, or maybe we can, make it like that smaller. And then let's create a new file and call it linear regression example.py. And this particular example is greatly inspired from an example on Scikit-learn. So we will also use their dataset as that. Similar to before, to the Streamlit example, let's first start by importing all the necessary packages. So we're going to need NumPy, or maybe let me close the file explorer. So we need NumPy as NP. We need, so actually we would also need Matplotlib, but since it does not work, let's try to do it with Plotly. So plotly.express SPX. If you want to prefer Matplotlib, then of course go for Matplotlib. And then we need to import the following. So we need from Scikit-learn. Scikit-learn is Scikit-learn. We're going to import data sets and linear model. And then we also need certain metrics. So from Scikit-learn import metrics. So maybe we can also move that up here to import it together with the others. So these are kind of like submodules similar to the optimization and stats from SciPy. And then let's have the main switch. So let's say if name equals main. So this was again necessary in order to have the file not being executed when it is imported. I mean, in our case, it's not too relevant, but here in that case, it's fine. Here in that case, why not have it? And then we want to use a data set that's called the diabetes data set. And we can load it by using the datasets functionality, and then have datasets.load diabetes. I mean, it's a little weird to say load diabetes. And we want to return it in XY fashion. And this XY is like a common convention in Scikit-learn to call your input to the model capital X and your output to the model lowercase y. And I want to call this diabetes, diabetes X and diabetes Y. Okay, let's first print out the data for a second. Or let's look at the shape of the data. That might be more relevant. So we expect these to be NumPy arrays, but let's see what the shape is. So let's say print diabetes x.shape and print diabetes y.shape. And then I will open up a new terminal here. And it already entered in my corner environment, but I'm reactivating it either way. And then you can either hit the play button up here, or you can type out Python linear regression example.py and then run it. Okay, and then we see that the X set, so the input to our model, is of shape 442 by 10. And if you remember, we kind of think of this tabular data. So we have 443 rows, 443 rows, and 10 feature dimensions. And then we have correspondingly 441 target samples. So basically, this is the Y here. So in essence, we would be interested in finding a mapping from 10 dimension to 1 dimension. Here, of course, for this particularly introductory example, we will only be looking at 1 dimension out of this. And therefore, I want to extract. So let me call this diabetes X extracted. and say that this will just be diabetes X accessed at all rows, but the second column. And then if we print the shape of diabetes X extracted, we will see that this will just be 443. Well, and then now that we have this one-dimensional input and one-dimensional output, let's look at the data and make a quick visualization. So let's create a figure by saying px.line, and then say X is going to be diabetes X extracted, and Y is going to be diabetes Y. And then we can call figure.show in order to bring up a web browser. Okay, if we run that, let's see about that. Okay, yeah, works. And then we bring up the web browser. And of course, it is a line plot because I failed here. It should, of course, be a scatter plot. Let's do a scatter plot instead. So I will bring that over. And we can change that to a scatter here. And nicely, of course, the interface to Plotly in that particular case is identical. So let's save the file and run it again. And then we have a scatter plot. I will let you give you like a second in order to follow up. So last time when we had this kind of example, we realized that that I actually did not know what the axes were. So we looked at the data set, and of course, earlier I said know as much about the data as possible, and I didn't know anything at all. And here it would be interesting. Maybe someone of you is kind of familiar with this field. So there must be some input from minus 0.1 to 0.1, and then we might have some output that lies in the range of 100 and 300. Maybe it's something like blood sugar. I don't know. So if you have something, then please let us know in the Zoom chat. Otherwise, we kind of nicely see the we kind of nicely see that there is some sort of a linear dependency. I mean, it might not be as obvious in the first place, but we kind of see the trend that the higher the X value, the higher the Y value, and we could approximately find a line in here. Okay, so we will later then do the proper splitting between training and test, but let's just first start to get a very first linear regression running. And for this, let us instantiate. So let's bring up a super simple regression model. So I will comment out these two lines. By the way, if you haven't done that before, you just highlight both, and then on Windows, on Linux, it's control hashtag. Whereas I think on Windows, no, that's the shortcut on Windows, and on Linux it should be Control-Shift/. And then you can comment out lines. And let's instantiate an object and call it a linear regressor. And for this, we will use linear model.linear regression. If you remember, I already showed you the interface to linear regression a couple of times over the last 2 days. And here we kind of define the so-called hyperparameters to a machine learning model. Hyperparameters, that looks like something like it's super special or something made up, but it makes sense in that sense because machine learning is an optimization over parameters. The parameters which define how we make that optimization over parameters are therefore called hyperparameters because they parameterize the optimization over the parameters. And those are the hyperparameters. So here we have, for instance, the fit intercept. That does not greatly matter here. It matters much more when we then look at more advanced examples, but just to be aware that those exist here. This is our linear regressor. And then in order to train the linear regressor, so this is what we want to do with machine learning models in order to train them, they did learn something. We do linear regressor dot fit, and fit like fitness, we provide it with supervised data, and in that case it is diabetes X and diabetes Y. And let's just run that and see if that works. I mean, let's hope for it and try to execute that. well, that kind of works. That's super interesting. I did not expect. Yeah, of course, because we'd use diabetes X. How stupid of me. We should, of course, use diabetes X extracted because we want to have the relation from this one-dimensional input to this one-dimensional output. So let's hit Control S to save it and then execute it again. And now it should raise an error. Exactly. And this error, of course, appears because go up. There's a lot of stack tracing here. And the error, of course, appears because our input is not a two-dimensional array or a two-axis array. And that is, of course, because we opted to select only one out of the 10 axes that our input X has. And this is problematic because the interface to, I think, almost all Scikit-learn algorithms that work with tabulated data requires us to have a tabulated data. But that's not a big problem because I think that's probably the first issue everyone runs into when they use Scikit-learn. It already provides us with a solution. So it says, it doesn't say it explicitly, but we provided Scikit-learn with something that is arbitrary. And so it recommends us to reshape your data either using array.reshape -1 if your data has a single feature, or reshape 1 - 1 if it contains a single sample. And that's, of course, because we follow the convention that in the rows, so the 0th axis, we have the number of samples, and in the columns, we have the number of features. So basically what we have to do is we have to use the first recommendation because we have only one feature, but we have a couple of samples. So let's add a dot reshape -1 in here. Okay, let's run it. And then we should be good to go. It was fitting our linear regression model. And now we have this model found. And I talked about parameters, so the parameters to our machine learning model, but what are they? And of course, if we take a look at our data once again, what is the typical parameter of a machine learning model? But here we have to look at the parameters of a linear regression. And of course, if I quickly head over to the slides for a second, the parameters of the machine learning model we're looking at here are the slope and the intersect of our function. So it is kind of that one here, which is, for this particular example, it's at 5. And then the slope, which is kind of how much we go to the right and up. So kind of this angle here. And these are the parameters that our model finds, or that our training procedure finds. And we can maybe print them out for a second by say print linear regression dot coefficient. And there's this convention in Scikit-learn, a parameter or an attribute to this particular object has an underscore at the end when it refers to a fitted parameter. So a parameter that has been fitted by the training procedure. And let's do the same thing for the intercept. So intercept is, so basically this is the M of linear regression. So this is the M in M times X plus N. And this will be the N in M times X plus N. And then we can execute that. And then here we see, well, we have found here a slope of 949 and an intercept at 150. Of course, let's take a look at our model here. There's a question in Slido. Someone is having an import error. I think probably you should be doing import from Scikit-learn or sklearn, import datasets, linear model, and metrics. I don't know, maybe you still used the stats from SciPy before. So I think it should be fine if you copy that down. And in case, and you should have installed linear regression in case it's not the case, linear regression, Scikit-learn. In case that is, if that is not the case, you can, of course, always install that with pip install scikit-learn. I hope that solves the problem. Okay. So we now see that we have found these parameters to our linear regression model, and it would now be interesting to kind of plot them as a line on top of our scatter plot. Okay. And for this, let's take a look at the scatter plot that we have here. So let's see, we want to draw a line in here. And for this, in order to draw a line, I mean, technically we would only need like 2 points, but let's just take a bunch of those points and then draw it on top. And for this particular case, let's take points from -1 to, minus 0.1 to 0.2. So let's create something, let's say maybe x eval is going to be np.linspace, so not linear, linspace from -0.1 to 0.2, 100 points. I mean, as said, technically we would only need 2, but let's do 100. And then we can query our linear regression at those particular points in order to find where the line lies. I mean, if that sounds a little bit weird, then stick with me for a second, and then I think it becomes clear. Let's say y eval for evaluation is going to be linear regressor dot predict, and predict is just a method in scikit-learn in order to, well, yeah, to take unseen data and use our fitted model against them. And here we want to use x eval. But again, sorry, not eval, x eval. And here we want to again use the, but here again we would run into the same issue with the reshaping, since the input to this machine learning model shall always be tabular data. So we have to reshape it, x eval reshape, and then -1, 1. So let's see if that just runs. Yep, that's fine. So it runs through, but now we have to create a scatter plot and draw a line on top of that plot. And I mean, we haven't looked at that in Plotly, and I must admit to you that as of right now, I also don't know that by heart. I have some suspicion how it might work like, but I could be wrong about that. So I will just try what I think it's going to be, and then we just figure it out together by Googling for the documentation. So for this, I will first want to move this scatter plot maybe below that, and then we can uncomment it. And this is drawing the scatter plot of the original ground truth data that we have. And then on top, I think it's called fig.add trace. We will see. We're going to add a trace of a line plot where x is x eval and y is y eval. But let's see. Maybe it works. Maybe it doesn't. Probably it does not. Yeah. Oh yeah. Of course, it shouldn't be fig.line. It should be px.line. Let me check if that helps. Well, then let's go for this example here. Of course, this might not be a little bit more difficult. Probably in Matplotlib, this would have been a bit more intuitive. And I'm pretty sure this is also not the best way to do it here, but at least let's follow the example that they provided here on Stack Overflow. Of course, I will come back to the predict and the reshape in a second, don't worry. So let's just add the trace by using the px.line on this one, and then we're supposed to use select traces, apparently. Okay, and then we need a list. Well, this is really, really complicated. Let's hope that this one works, so that we at least have that one down. Still not the case. Okay, yeah, sure. We need to use add traces. Okay, finally. has a different color, but at least it works now. Great. Sorry that this is so improvised. Okay, I will come back to the questions in a second. I just want to leave the continue on the thought. So this blue line on the blue dots is marking our regression line that we found. So this is supposed to be the line which balances like these springs going from the point to the line. And you also see that, I mean, just by an I norm, it kind of looks good. It kind of looks like it just has found a good regression in this linear regression sense. Of course, this is like the I norm. So next step would be to look at some metrics in order to understand what is truly going on here. But before that, I want to address the questions. So let me move that over here. And first question, can you explain again what's predict? Of course. So this was a little fast. So the predict is basically querying the machine learning model. So recall in the so maybe let me move back to the slides for a second. When we looked at the idea of machine learning as some sort of this input-output pair, we have two different stages in machine learning. So often those are called as a training stage, and then we have an inference or evaluation or prediction stage. And for the training stage, we are taking, in the supervised example, we are taking pairs of input-output. So we have these 442 points from the diabetes data set for which we know how X corresponds to Y. And then in a training step, we're using these points in order to train the model. And then there might be steps where you want to infer new predictions. So for instance, you might then be interested in saying, well, I now have a patient which has this X value of 0.3222. To what kind of a Y value does that correspond? Because in the inference stage, you do no longer have the information, which is the corresponding Y value. And so the goal is to predict new unseen results from our data. And that's basically what this predict is doing. And you can also, this becomes also clear by analyzing the interface. So for the fit interface in our supervised learning example, we provided an X and a Y. So this is kind of giving it the information to learn from. And then we have a predict, which just takes an X. Obviously, of course, it doesn't take a Y. And if you look at the interface, so we call the fit function and it does not return anything. Whereas here, if we call the predict function, it returns the predicted values. And this also, I hope that shined some more, gave a more light on the on this prediction. This also naturally leads to an idea of this reshaping. So it's kind of a convention in Scikit-learn, not kind of, it's a convention in Scikit-learn. So if you have data, so well, maybe let's go to how should we do that? Maybe let's go to an interactive Python session for a quick second. So let's open up IPython, and then let's have import numpy s and p. And then, for instance, let's do x equals numpy. What should we do? Let's do numpy.random.rand free, and then we have kind of an array with 3 entries in here. And an array with 3 entries can either be thought of as a column vector or as a row vector, or in other words, it can be thought of as a matrix with 3 rows and 1 column, or 1 row and 3 columns. So maybe also like graphically speaking, so you can either have, so if you have a collection, so if 0.3, 0.7, 0.9. You can either represent this as a column vector, 0.3, 0.7, and 0.9, or you can represent this as the row vector, 0.3, 0.7, and 0.9. If you view that as a matrix, like a tabular matrix, then this one would be interpreted as a data that contains 3 samples, so 3 samples, but only one feature each. And here we only have 1 sample with 3 features. And basically this reshape is adding this proxy dimension. So basically also what we saw yesterday with the broadcasting. So if we go here, this reshape -1,1 basically does the following: move all the dimensionality into the first or 0th axis, and then add a proxy axis with only 1 dimension. And we need that whenever we interface with scikit-learn algorithms, since X has to be matrix-like. I hope that answered the question. I will take off these 2 questions. If it's still unclear, then please ask a follow-up question. So as said, we now saw that our model kind of performs well, let's say, from an I norm, but now we also want to use some metrics in order to investigate that. And for this, we loaded the metrics package because scikit-learn provides many different metrics. And in order to have a meaningful analysis, it might be interesting to look at the performance on data it has not seen before. So let me see. What is a good way to do that? Okay, well, let's maybe rename our variables a little bit. So we have this diabetes X and we have this diabetes Y, and we now want to, well, how should we do that? Best case. So let's follow up and just call it an X test and an X train. And we will now slice off certain parts of our diabetes array, in that sense, that we correspond to test and train data. And just for the sake of simplicity, we will use the, or maybe, let me check. Maybe it's better to do it that way. So that we will define X train first and say that X train is going to be our diabetes X extracted, and it's a one axis array, and then index it at the first points all the way up to the last 20 in that sense. Maybe let's go a little bit higher and do the last 50. So remember, our data set has 442 entries. And with this syntax, we are taking all the entries up to the 50th last entry. And we associate that to our training data set. And the rest of this data set shall be associated to the testing. So we do X test is going to be diabetes X extracted minus 50 all the way to the end. So we kind of have this, maybe if we, I don't know, maybe put it like this. So this basically means take all the data points up until the minus 50th, so this 50th last, and then take from the 50th last all the way to the end. So we have now 50 entries in the test data set, and the train data set must be 442 minus 50, which will equal approximately 390. And we can do something similar on Y, which is our, let's say, our target variable. And then we have Y train is going to be diabetes Y at these all the way to the 50th last element. And then a Y test is going to start, it's going to start at minus 50 all the way to the end. Okay, then we also have to adapt, of course. Maybe let's comment out this shape printing, and then have our linear regressor being fit on the training data set. So xtrain. And then here we also have to do it on the ytrain. So train for training, of course. And here we used these xeval to create our line. And now we want to do another prediction, but on the test set in order to evaluate our metrics. So let's comment out the figure for a second, such that it's not shown when we re-execute it, and then let our linear regression predict on the test part, so on the test part of X. So we do y test predict and say this is linear regressor dot predict on X test dot reshape -1, since we have to bring it again into this tabular data form. Okay, and the reason we did that is that we basically now have a collection of y values that our model predicted, and we have a collection of y values where it actually should be. So we have the ground truth and the prediction, and this allows us to evaluate how good it is. So I mean, it's kind of if you take an exam, and of course there's a reference solution and then there's your solution, and if you compare your solution against the reference solution, you can figure out how good you are, or I mean, the examiners figure out how good you are. So let's compare some error metrics, and a classical error metric is the mean squared error. And for this, we use metrics dot there are multiple errors available, or multiple error metrics here available, but here we want to use the mean squared error, and here we want to apply it on the prediction and then the ground truth, or maybe it says the other way around, but for the mean squared error it does not matter, but let's stick to the interface and say it says y true, so the ground truth, so the reference solution to the exam, and y predict, that is what our model predicted. So let's have y test predict and y test. And that gives us the mean squared error. And then let's print it and use a formatted string and say mean squared error is going to be the mean squared error, and let's use a floating point format specifier with 4 digits of precision. And now if we save the file, we can re-execute it, and I hope there is no error. Let's check. No, there's not. And here we have our mean squared error, which kind of gives us an estimate of how well our fit is. And of course we have to, I mean, this kind of sounds like, looks like a large value in this particular case, but here we have to keep in mind that in this scenario, we're looking at values. Let me bring over the plot again. We're looking at values that have a large order of magnitude. So the error always have to be taken with a grain of salt in that regard, since if you are working with large numbers, or if you're predicting large numbers, you will also get large error metrics. Luckily, there are more error metrics that are independent of the order of magnitude. And the classical example is to use an R2 score, which is the coefficient of determination. It has some a statistical interpretation, but for all practical perspective, we just see that it's kind of a value between minus infinity and 1. And if it is really close to 1, then we have a good, then we did a good job. So let's do R2 is going to be metrics dot R2 score on the y. Oh, actually, I did it the other way around. So it should be y test and this one y test predict. But as said, for the mean squared error, the order does not matter. So here it is y test and y test predict. And then we can do something similar and say print formatted string R2 score And here we get R2, and let's have, again, similar floating point precision. And if we run that, then we get our mean squared error, and we get our R2 score, which is around 0.4. And it's kind of a decent fit for this particular example. Okay, we will look at this example in more detail tomorrow again. Let me just quickly recap what we've done so far. So there's a couple more things that we will be doing tomorrow. So first of all, we have loaded some data set. Of course, if you want to apply these kind of algorithms, or maybe let me close that so that you can see it in its entirety. That's kind of hard. So we first loaded this artificial data set. And of course, if you want to apply these to your own problems, then you of course need to load your own data. But you will also see that tomorrow when we look at some other example data, and we have manipulated our data set a little bit in that we extracted only one of its 10 feature dimensions. We then selected the first about 390 data points to be part of our training data set, and the last 50 points to be part of our testing data set. And we used training and testing in order to then test for, or to analyze the generalizability of our model, which means that if it also performs well on data it has never seen before. And then the 2 points I want to keep, I would like to keep in mind is that the application of scikit-learn algorithms is always kind of a 3-step process. So the first step is always an instantiation of the model or the algorithm that you want to use. Then we have a fitting. So this is the training, this is the learning in machine learning. And then we have a prediction, which is a usage of the model. It's kind of like, I don't know, maybe if we have the relation to the exams, then maybe this instantiation would be the start of the semester. And then the fitting is kind of what you do during the semester. And then the prediction is what you would be doing in the exam. So when you're asked to perform on previously unseen examples. And then we looked at some visual comparison, so that we kind of eyeballed it and saw that, oh, well, the line is kind of good, but with some more concrete estimates, so some concrete error estimates, we could have also determined that it's a good fit. I mean, tomorrow we will look into more detail on how to clearly say that we are happy with our fit. But here that's already leading us into the right direction. This is also now towards the end of today's course, today's part of the course. And as said, tomorrow we will continue with scikit-learn. I think we will make a good progress and probably can go over all the examples and then start into deep learning. But before we do that, I would probably ask you again tomorrow if there is something that you want to go over once again, instead of moving on to more complicated examples, in case something is left out that you find is particularly relevant for you. Then based on that, since Jan is not here, I will close off for today and hope you can rest a little bit, and we see each other again tomorrow then when we continue as said with scikit-learn. So thank you very much for being here today. I had a lot of fun and hope you had too. And then we see each other at 9 a.m.